Hey guys, good evening and welcome back again to your Unacademy NEET English channel. Hope all of you are doing great, having a good time. So my dear students, quickly, just let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly, let me know in the chats with the thumbs ups. Everyone. Everyone, people, everyone. Welcome back, guys, welcome back. So give me some green signal from the chats so that I'll get to know I'm perfectly audible, visible to everyone. Good evening, people. Good evening, good evening. Good evening. Is the audio, video, everything perfect? I'm doing good, guys. I'm doing good. I'm doing good. Thank you. So quickly, let me know in the chats, is the audio, video, everything perfect, right? Because I don't want you guys to say in between the audio is not clear, the video is not clear, yeah? So just let me know quickly in the chats. And guys, call up all your friends quickly. We are going to start. Yes? Perfect, perfect, perfect. So my dear students, so first of all, as you all must be knowing, today it's going to be a one-shot session, a mega marathon from the chapter Solid State, right? The whole chapter I'll be covering in the today's session only. It will take almost 4 to 5 hours because it's not that big chapter. Every single thing I'll be starting from the basics itself, from the scratch. We'll cover the theory from the basics itself. Then in the same session itself, we'll be covering all the question patterns, all the problem patterns that can be asked from the chapter Solid State. And let me tell you, it's one scoring chapter, which is easy at the same time, right? Like whenever you see a question from the Solid State, it's always a doable question. There are not tough questions asked from this particular chapter as far as your NEET examination is concerned. Okay? Perfect. And before starting this particular session, the ones who have not liked yet, I would want everyone to like the session. Do share this particular video with everyone. Whosoever cannot afford the offline coaching, whosoever cannot afford the paid batches, this particular session is for every single one. Because we are not going to compromise on the content, even on the YouTube, right? And at the same time, if you have not subscribed to the channel yet, I would want every one of you to subscribe to this particular Your Unacademy NEET English channel as well. Perfect. So people, let's get going then. Let's get started with the session. Okay. Well, the first topic which we are going to cover here in the today's session, what is that going to be? That is going to be classification of the solids. Exactly, starting from the basic. So let's get going then. Let's start the first topic of our today's session, that is classification of the solids. Yeah. My dear students, as you all must be knowing, when we talk about a solid is definitely made up of the constituent particle, right? A solid is made up of the constituent particle. Now, based on the arrangement of constituent particles inside the solid, we classify solids into two categories. So let me write it for you. I would want you guys to take a note of every single thing, okay? I'll write based on the arrangement. Based on the arrangement of constituent particles. We classify solids into two types, right? The first category is going to be crystalline solid. And the second category is going to be the amorphous solid. So based on the arrangement of constituent particles inside a solid, we classify solids into two categories. One is going to be your crystalline solid, another one is going to be your amorphous solid. Now, what is the difference between the two? My dear students, when we talk about the crystalline solids, in case of crystalline solids, we have got a regular arrangement, or you can say definite arrangement of constituent particles. We have got a regular arrangement or definite arrangement of constituent particles. And when we talk about the amorphous solids, there is irregular arrangement. There is irregular arrangement of constituent particles. So first of all, what these two things exactly means? My dear students, I'm going to draw one simple arrangement over here. Let's say this circle, it represents constituent particle of a solid. And there will be a lot of constituent particles inside the solid, right? I'm going to make one arrangement. Just understand carefully what exactly I'm talking about. Try to understand carefully. Let me call this constituent particle as A. Let me call this as B. Again, this is A, this is B. This is A, this is B. This is A, right? Everywhere I'm writing A, B, respectively. Try to understand what exactly I want to convey. Over here, one more arrangement I'm making of the same constituent particles. I'm making one more arrangement of constituent particles. Try to identify the difference between the two arrangements. I'm calling this as constituent particle A. Let's say this is A, this is A, this is B in between, for example. This is B in between, this is A, this is B, right? I'm randomly marking A and B over here. I'm randomly marking A and B over here. Now, guys, I want you guys to understand one simple thing. If you look at this particular arrangement, let's assume we have got a solid which is made up of two constituent particles, A and B, right? This is one arrangement which is inside the solid between the constituent particles. If you look at this arrangement carefully, after every A, B is getting repeated, after every B, A is getting repeated. Everywhere. After every B, A is getting repeated, after every A, B is getting repeated. So can I say this is the definite arrangement? This is the regular arrangement of constituent particles inside the solid? Yes, this is the regular arrangement. This is the definite arrangement of constituent particles inside the solid. And whenever you see this kind of the arrangement, a definite arrangement, a regular arrangement of constituent particles inside the solid, you call that particular solid as the crystalline solid, right? Now look at this particular arrangement. Over here, as you can see, we have got 3A particles. Then suddenly 2B particles came. Then 1A particle, 1B particle, A, then 2A. There is no regular arrangement as such in this particular solid. There is no regular arrangement of constituent particles as such in this particular solid. And whenever you see such kind of a solid in which there is irregular arrangement of constituent particles, you call that particular solid as the amorphous solid. As simple as that. So one simple thing which differentiates both the solids. In case of crystalline solid, we have got regular arrangement of constituent particles. In case of amorphous solids, we do not have regular arrangement of constituent particles. We have got irregular arrangement of constituent, right? Point number one. Point number two, when we talk about the crystalline solids, they have got sharp melting points. Whereas, when you talk about the amorphous solids, they melt over a wide range of temperatures. They melt over a wide range of temperatures. They melt over a wide range of temperatures. Now, you must be thinking what it means exactly. My dear students, when you want to melt a crystalline solid, in order to melt a crystalline solid, you have to increase its temperature, right? You have to supply heat. You have to increase its temperature. Perfect. My dear students, in case of crystalline solids, all the attractions between the constituent particles, they are uniform. All the attractions between the constituent particles, they are uniform. Therefore, all the attractions are broken at a particular temperature. All the attractions are broken at a particular temperature in case of crystalline solid. And any such solid in which all the attractions are broken down at a particular temperature, we say that solid has got the sharp melting point. Whereas, when you talk about the amorphous solids, there isn't uniform force of attraction everywhere. There isn't uniform force of attraction between two constituent particles everywhere. No. So when you want to melt it, you'll be raising its temperature. And let me tell you, all the attractions, they are not broken down at a particular temperature. For example, few attractions here in this solid, right? Few attraction between the constituent particles in this solid. Let's say they get broken down at 80 degree. Few attractions get broken down at 90 degree. Few attractions get broken down at 100 degree. That means this particular solid, it does not melt at a particular temperature. It melts over a wide range of temperature. Okay? So let me tell you, this is one more important difference between crystalline and amorphous. When you talk about the crystalline solids, they have got sharp melting points. That means all the attractions are broken down at a particular temperature. But when we talk about the amorphous solids, in case of amorphous solids, all the attractions, they are not broken down at a particular temperature. Your amorphous solids, they melt over a wide range. Okay? Now, one more important thing about the crystalline solids. My dear students, crystalline solids, what do? We call them as the true solids. We call them as the true solids. Whereas when you talk about the amorphous solids, we call them as the pseudo solids. We call them as the pseudo solids, or you can call them as super cooled liquids. You can call them as the super cooled liquids. Now, why these amorphous solids, they are called as the super cooled liquid? My dear students, when you talk about the constituent particles of the amorphous solids, they have got tendency to show moment. And crystalline solids, their constituent particles, do not show any sort of moment. For example, let me give you an example. For example, if you talk about a glass window at your home, right? Glass window at your home. When you see the same glass window after 30 years, you'll observe one thing. You'll observe the thickness of the glass at the bottom would have got increased. And the thickness of glass at the middle, that would have decreased. Thickness of the glass at the bottom would have increased. And thickness of glass at the middle, that would have decreased. Can you think what is the logic? The logic is some of the constituent particles of the glass at the middle, they have traveled down and they have got settled at the bottom. Due to which, at the bottom, the thickness of the glass would have increased and the thickness of the glass in the middle, that would have decreased. Perfect? The glass, that is the perfect example of the amorphous solid. Can I say the constituent particles of the amorphous solids, they have got the tendency to show moment. They have got the tendency to flow, right? And any such solid whose constituent particles have got the tendency to show moment, to flow, what do we call that particular solid? We say that particular solid, either you'll be calling it as pseudo-solid or you can call it as super-cooled liquid, right? Whereas, if I talk about the crystalline solid, when you talk about its constituent particle, they do not show any sort of moment at all, right? Perfect. So that's why we call this particular solid as a true solid. Okay. One more important thing, my dear students. When you talk about crystalline solids, they show clean cleavage. They show clean cleavage when cut with knife. And they do not, amorphous solids, they do not show clean cleavage when cut with knife. What is meant by that? Imagine that this marker, imagine that it's a crystalline solid. Just imagine. Okay? Imagine that it's a crystalline solid. When you cut this crystalline solid with a knife, you'll be getting two pieces of it. The two new surfaces which are getting exposed, right? When you cut it with knife, two new surfaces will get exposed. If this marker is a crystalline solid, the two new surfaces which are getting exposed, they'll be smooth, they'll be polished. They'll be smooth, they'll be polished. I'm talking about the crystalline solids. When crystalline solids are cut with knife, the new surfaces which get exposed, they'll be smooth, they'll be polished. And whenever you see such kind of a solid, which when cut with a knife, the new surfaces which get exposed, if they are smooth, if they are polished, then we say that solid shows clean cleavage. Whereas if I talk about amorphous solids, it does not show clean cleavage at all. When amorphous solid is cut with a knife, The new surfaces which get exposed, they won't be smooth, they won't be polished, they'll be irregular, right? Yes, as simple as that. My dear students, at the same time, one more important thing about crystalline solids, they show, what do they show? They show regular geometric shapes. They have got regular geometric shapes. Whereas if I talk about the amorphous solids, they do not have the regular geometric shapes. They have got irregular shapes. Irregular shapes. Their shape can be anything. Whereas when you talk about crystalline solids, their shape is always a regular geometrical one. It can be cubical. It can be hexagonal, right? Whatever regular geometric shapes we have, right? Your crystalline solids, they show regular geometric shapes. Whereas AC is not working, just a second. Whereas when you talk about the amorphous solids, they do not show the regular geometric shape. I hope it's clear, right? The basic few differences between crystalline and amorphous. One more important thing, one more clear-cut difference between the two. My dear students, crystalline solids, they are anisotropic in nature. They are anisotropic in nature. Whereas when you talk about amorphous solids, they are isotropic in nature. Now you must be thinking, what is meant by anisotropic and isotropic? This is one more important property. Have a look. For example, this is the crystalline solid, right? Let's say I want to measure a physical property of this crystalline solid. Physical property, for example, refractive index. Imagine that I want to calculate refractive index of this solid. Refractive index, that is the example of physical property. So imagine that I want to calculate the physical property refractive index for this crystalline solid. What I'm doing exactly is I'm choosing this direction and calculating the value of refractive index for this solid. Okay. Then I'm changing the direction. Then in this particular direction, I'm measuring the refractive index. Right? What exactly I'm doing? I want to calculate. I want to measure a physical property like a refractive index for this solid. Now I have chosen two directions. First, I'm measuring the refractive index in this direction. Then I'm measuring the refractive index in this direction. My dear students, if you observe, when you are measuring the refractive index in this direction, can I say the value of refractive index will be due to BA interactions, right? And when I choose this particular direction, can I say the value of refractive index will be due to AA interactions? Just to make you understand. So basically the point is, in case of crystalline solids, when you measure a physical property, the value of physical property, it changes on changing the direction. The value of physical property changes on changing the direction. Okay? Whereas when you talk about amorphous solids, whatever direction you want to choose, you can choose any direction and measure the refractive index. In every direction, the value of refractive index, the value of physical property will come out to be same due to the irregular arrangement of constituent particles. I hope it's again clear to you. So do remember this particular point as your crystalline solids, they are anisotropic in nature. The value of physical property changes on changing the direction. Whereas your amorphous solids, due to the irregular arrangement of constituent particles, the value of refractive index, it does not change on changing the direction. Quickly, let me know in the chats with the thumbs ups if it is clear. Quickly, people. Quickly, in the chats with the thumbs ups if everything seems clear till here. Yeah? All the things are clear? Quickly, say yes or no in the chats or give me the thumbs ups in the chats. I'll get to know that it's definitely clear to you. Quickly. Quickly, my dear students. Till then, I'm going to mark a statement over here. Yeah, all clear? Perfect. Perfect, people. Perfect. All right. So I have written a statement over here that crystalline solids, they form a crystal lattice. Now you must be thinking, what crystal lattice is all about? I'm telling you crystalline solids. The ones where you see the regular arrangement of constituent particles. This crystalline solid, it forms a crystal lattice. Now the point is, what is a crystal lattice? What is a crystal lattice, you must be thinking, right? So let's have a look on what is meant by the term crystal lattice. Crystal lattice, what is it? It is defined as the regular arrangement. It is defined as the regular arrangement of constituent particles. The regular arrangement of constituent particles in three-dimensional space. In three-dimensional space. Inside the solid. Inside the solid. My dear students, well, when we talk about crystalline solids, inside the crystalline solid, what do we have? We have constituent particles, right? Whatever regular arrangement of constituent particles will be there in three-dimensional space inside the solid. That regular arrangement is something which you call as crystal lattice. Now, what is meant by that? Have a look exactly what I'm talking about. For example, I'm making a cube over here. Imagine that I'm making a cube over here. And my dear students, at the corners of the cube, I'm keeping the constituent particles. I'm keeping the constituent particles. Imagine that you have got a crystalline solid in which the constituent particles have got this kind of arrangement. This kind of arrangement. Imagine that inside the crystalline solid, the constituent particles have got this kind of arrangement. Should you be calling this arrangement as the regular arrangement of constituent particles in 3D inside the solid? Yes, you'll be calling it as it's a regular arrangement of constituent particles in three-dimensional space inside the solid. As you can see, whatever is the distance between these two particles, same is the distance between these two particles, same is the distance between these two, same is the distance between these two. So this is the regular arrangement of constituent particles inside the solid in three-dimensional space. And let me tell you, any such regular arrangement of constituent particles in three-dimensional space inside the solid, that's what you call as crystal lattice. So I would say this is one type of crystal lattice. This is one type of regular arrangement of constituent particles, right? There can be one more as well. For example, if I make an arrangement like this, you tell me whether it's right or wrong. Let's say I'm making one arrangement like this. These are the constituent particles which I'm keeping over here at the corners. And now at the same time, let me join them. So my dear students, do you see over here, it looks like an hexagon? Yes, it looks like a hexagon. Imagine that the constituent particles inside the solid, they have got such kind of the arrangement. All these circles, they represent the constituent particles. Imagine that you have got a crystalline solid in which the arrangement of constituent particles looks like this. They are forming a kind of hexagon over here, right? So this is one more regular arrangement of constituent particles in three-dimensional space inside the solid. So this is something which I'll be calling as crystal lattice again. So this is one more type of crystal lattice. Perfect. So I hope you got the idea of what crystal lattice exactly is all about. Crystal lattice is nothing. It is just the regular arrangement of constituent particles in three-dimensional space inside the solid, right? Yeah. Now, my dear students, understand. I'm writing one statement over here. The statement is simple. I'm writing your crystal lattice. Crystal lattice. It is composed of unit cells. Now a new term came over here, that is a unit cell, right? Now let's try to understand what unit cell exactly is all about. Let's write the definition of the unit cell so that you can understand it properly. Unit cell, it is defined as the basic structural unit. The basic structural unit. The basic structural unit which upon repeating which upon repeating generates the entire crystal lattice. The basic structural unit which upon repeating generates the entire crystal. Let's try to understand what it exactly means. See guys, have a look. Imagine that the room in which you guys are sitting right now. Imagine that the room in which you guys are sitting right now, in which I'm standing right now. Imagine this room is cubical in shape. Okay, this room is cubical in shape. Perfect. Let's call this room as the crystal lattice. Let's call this particular room in which I'm standing right now. Let me call it as the crystal lattice. Okay, it's a crystal lattice. So can I say this particular room is actually made up of bricks? Yes, this room is made up of bricks, right? Can I say when one particular brick got repeated along x-axis, along y-axis, along z-axis, then only the whole room got generated? Can I say something like that? On repeating one particular brick along x-axis, along y-axis, along z-axis, then only this whole room got generated. So can I say that brick is actually the basic structural unit, which upon repeating along x-axis, along y-axis, along z-axis, generates the entire room? What was the room? The room was the crystal lattice. What is the brick? Brick becomes the unit cell of the crystal lattice. I hope I'm clear with this. I hope I'm clear with this. Quickly. Quickly, guys. Let me know in the chats. Is it clear? Yeah? So, I hope both the terminologies are clear. One is crystal lattice, one is unit cell. So, crystal lattice, it is composed of what? It's composed of unit cells. Okay? Let's try to understand this a bit more in detail. My dear students, for example, understand this particular diagram which I'm representing. Let's say I'm making one cube over here. Let's say this is one cube. Okay, this is a cube. Perfect. Right? Let me call this whole cube over here as crystal lattice. So what is this cube? It's a crystal lattice. Okay, it's a crystal lattice. Dear students, understand what exactly I'm doing. Understand exactly what I'm going to do. Understand exactly what I'm going to do. Okay. The bigger cube over here, that's something which I call as crystal lattice. Can you let me know? Can you let me know of how many small cubes this bigger cube is made up of? Can you let me know of how many small cubes this bigger cube is made up of? As you can see, if you want to have a look over here, see, let me highlight one particular cube, one particular small cube over here. I'm just highlighting one particular small cube. I'm just highlighting one particular small cube. This is the highlighted small cube over here, right? This is the highlighted small cube. My dear students, imagine that we have got two floors over here. This floor is the ground floor and this floor is the first floor, okay? So in the ground floor, how many small cubes do you see? This is one cube. This is one small cube, right? This is one small cube. Just behind it, there will be one more small cube whose top surface is this one. Whose top surface is this one. On the side of it, there is one more small cube whose top surface is this one. And behind this particular small cube, there is one more cube whose top surface is this one. Okay. So in the ground floor, how many small cubes we have? In the ground floor, we have got 4 small cubes, right? So these four top surfaces, these 4 surfaces which I have highlighted, can I say the same 4 surfaces? They are the bottom surfaces of the 4 more cubes which are at the top. Yes, right? So 4 cubes below and 4 cubes above. So in total, how many small cubes are there? There are in total 8 small cubes, right? So this bigger cube, it is made up of 8 smaller cubes. Can I say, on repeating this particular small cube, upon x-axis, upon y-axis, upon z-axis, the whole crystal lattice is generated, right? So can I say, this smaller cube It is the basic structural unit, which upon repeating along x-axis, along y-axis, along z-axis, it generates the entire cube. Perfect. So this smaller cube, should I be calling this as the unit cell? Absolutely, I'll be calling this as the unit cell. So what is the unit cell exactly? A unit cell is a basic structural unit, which upon repeating along all the directions, along x-axis, y-axis, z-axis, generates the entire crystal lattice. So I hope you got the idea of what exactly this unit cell is all about. Okay. Now, my dear students, in this particular chapter, we have to analyze these unit cells in detail. We have to understand these unit cells in detail, right? By the way, the session PDF, the handwritten PDF you'll be getting on this Telegram, t.me/WASSIM This is one Telegram, right? There is one more, that's Unacademy's official NEET English Telegram. You'll be getting the PDF in that Telegram as well. Okay? Perfect. Now, people, the point is, how many different types of unit cells are there? Types of unit cells. There are many types of unit cells, but over here we are just going to discuss 3 unit cells. I'm not discussing the unit cells right now in detail. I'm just giving you the idea of things. Okay? And afterwards, we'll be discussing them in detail, okay? So, dear students, the first unit cell is what you call as simple cubic unit cell. Simple cubic unit cell. Or you call it as the primitive unit cell. You call it as the primitive unit cell. You can represent it by SCC, simple cubic unit cell. This is the first type of unit cell which we have. Okay, this is the first type of unit cell which we have. Simple cubic unit cell. Now, there are few points which you need to know. There are few points which you need to know about simple cubic unit cell. And what are exactly those points? Let's try to understand. And please do remember all those points which I'm telling you now. Okay. So first of all, when I talk about the simple cubic unit cell, do remember the constituent particles. The constituent particles. They will be present. The constituent particles, they'll be present only at the corners of the cube. Only at the corners of the cube. Point number 1. Point number 1. What it means, you'll get the idea in some time. Point number 2. The contribution of the corner particle. The contribution of the corner particle towards a cubic unit cell, that is taken to be 1/8. Number 3. Adjacent corner particles. Adjacent corner particles. They touch each other in case of simple cubic unit cell. Now, what all these things exactly mean? Right? What is meant by all these things? Have a look, people. For example, I'm going to draw one simple cubic unit cell over here. Okay? So imagine that this is a cube. Imagine that this is a cube. And my dear students, since it's a cube, right? So what exactly I'm going to do? I'm going to keep the constituent particles of the solid only at the corners of this particular cube. Can I say this is the unit cell in which the constituent particles are only present at the corners of the cube? Yes. Right? This is the solid. This is the unit cell in which the constituent particles are only present at the corners of the cube. Whenever you see such kind of the unit cell in which the constituent particles will be only present at the corners of the cube, you'll be calling this particular unit cell as the simple cubic unit cell. Okay? So in case of simple cubic unit cell, the first point is the constituent particles are only present at the corners of the cube. Number 1. Number 2. My dear students, if I ask you whether this whole particle is inside this cube, you'll say no. This complete particle is not inside the cube. This particle over here, it is shared by 8 cubes. This particle, it is shared by 8 cubes. For example, have a look on this particular diagram. Let's say you have got a particle here. You have got a particle here. Can you let me know whether this whole particle is inside the smaller cube? No. This whole particle, it is shared by 8 cubes, right? It is shared by 8 cubes. 4 in the ground floor, 4 in the first floor. Perfect. So I must say this whole particle is not inside the smaller cube. Only its 1/8 part. Only its 1/8 part will be inside this smaller cube. So that's why we say the contribution of the corner particle towards the cubic unit cell, that is 1/8. So if I select this particular particle, only 1/8 part of it, only 1/8 part of it will be inside this particular cube, right? Okay. On this particular side, there'll be one more cube whose top surface is this one. Just behind this cube, you'll find one more cube whose top surface is this one. Just behind this cube, you'll find one more cube whose top surface is this one. Similarly, on the top, there'll be 4 more cubes. Perfect. So this particular particle, it is shared by 8 cubes. So its contribution towards our cube over here, that's going to be 1/8. That's going to be 1/8. Okay. This was point number 2. Contribution of the corner particle towards the cubic unit cell is 1/8. Number 3. Adjacent corner particles, they touch each other. Now, which particles you'll be calling as adjacent corner particles? My dear students, this particular particle and this particular particle, I'll be calling them as adjacent corner particles. This particular particle and this particular particle, adjacent corner particles. This one and this one, adjacent corner particles. This one and this one, adjacent corner particles. And all the adjacent corner particles in SCC, they'll be touching each other. That means this particular particle and this particular particle, they will be touching each other basically. So let me show it to you. Let's say this particular particle goes till here. And this particular particle, let's say it goes till here. Just to show, right? So adjacent corner particle in SCC, they'll be always touching each other. These are just 3 points which I would want you guys to remember about SCC for now. Number 1, the constituent particle is present only and only at corners. Number 2, the contribution of the corner particle towards unit cell, that's 1/8. Number 3, adjacent corner particles, they touch. Kirtana, this is the deleted chapter as per NCERT, but this chapter is not deleted yet by your NTA or NMC, right? There is no such notification as well. Perfect. It is deleted in NCERT. It's not deleted by your NTA or NMC as far as NEET is concerned yet. They might delete it, maybe or maybe not. You have no idea. Okay. So let's not keep any stone unturned. Yeah. Perfect. So this was the first type of unit cell whose basic idea you got. I'm just giving the basic idea now. I'm not teaching all these in detail now. The detailed analysis we'll do after. Right now, just the basics. Okay, the second unit cell. Second unit cell is what I call as body-centered cubic unit cell. Body-centered cubic unit cell. Right? It is represented by BCC. Now, in body-centered cubic unit cell, what exactly happens? Let's have a look what happens. So, dear students, in case of body-centered cubic unit cell, again 3 points you'll be remembering. Number 1, the constituent particles, they are present. They are present at the corners of the cube. Apart from the corners, they are present at body center as well. What that means, you'll get the idea in some time. Well, one more thing. The contribution of the corner particle towards the cubic unit cell, that's 1/8. Contribution of the body-centered particle towards the cubic unit cell, that's 1. Okay. One more important thing, then I'll show it to you. In case of body-centered cubic unit cell, do remember body diagonal particle. Body diagonal particles. What do? They touch each other. Let's get to know exactly what it means. Have a look, people. For example, I'm making a cube over here. I am making a cube over here. This is the cube. Imagine that this is the cube, right? Now, people, in this particular cube, what am I going to do? I'm going to keep the constituent particles first at the corners, and at the same time, I'm going to keep one constituent particle exactly at the center of the cube. Whenever you see such kind of the unit cell in which the constituent particles will be present at the corners as well as the body center, you'll be calling this particular unit cell as the body-centered cubic unit cell. You'll be calling it as BCC. Now, my dear students, one thing you already know, contribution of corner particle towards the unit cell, that's 1/8. Right? Now, if I ask you, what about the contribution of this particle? is this particular particle, the one which is at the center of the cube, is it shared between other cubes? No. It is just completely inside this cube. So its contribution towards the unit cell, it is exactly going to be 1. It's exactly going to be 1. Okay. Now at the same time, I told you a few minutes back, body diagonal particles, they touch each other. Now, what are body diagonal particles here? My dear students, look at the front face over here. Look at the front face and select this particular corner. Okay. This was the front face which I'm talking about. Now, talk about the back face. This is the back side face. Okay. And select this particular corner. When you join this particular corner with this particular corner, you'll be calling this particular line as the body diagonal. This is the body diagonal which we have. Right? This body diagonal, it passes through the body center. It passes through the body center. And let me tell you, all the particles which lie along the body diagonal, they'll be touching each other. Now you must be thinking, which all particles lie along the body diagonal? I would say this particular particle, and this particular particle. They lie along the body diagonal. So they should be touching each other. How exactly they should be touching each other? Let me show it to you. Let's say this particular particle is like this. The one at the middle is, for example, like this. And the one here, that's, for example, like this. So they are touching each other. So in this manner, these body diagonal particles will be touching each other in case of what? In case of your BCs. Okay? Perfect. So this was the quick idea of how this BCC looks like and what all parameters you have to remember for now. Okay? Similarly, we have got the third type of unit cell, which is again important. That's something which you call as face-centered cubic units. Face-centered cubic units. And this face-centered cubic unit cell you represent by FCC. This is how you are going to represent it, FCC. Now, 3 things you have to remember about this FCC as well. Okay, and what are the 3 things? Have a look. Number one. In case of FCC, the constituent particles, they are present at the corners of the cube. Apart from the corners, they are present at face centers as well. Apart from the corners, they are present at face centers as well. How it looks like, you'll get the idea in some time. Just wait for it. Number 1. Number 2. Contribution of corner particle, I've already told you. Towards the cubic unit cell, that's 1/8. Contribution of face-centered particle towards the cubic unit cell, that's 1/2. Okay. Now, dear students, in case of FCC, do remember face diagonal particles. Face diagonal particles. They touch each other. Face diagonal particles, they touch each other. Let's exactly see how it looks like. Have a look. Again, over here, I'm drawing a cube. Imagine that this is the cube, right? Imagine that it's one cube over here. And what I'm doing, I'm keeping the constituent particles, first of all, at every corner. I'm keeping the constituent particles, first of all, at every corner. And apart from that, I'm keeping the constituent particles at the center of each face. Yeah? Now, dear students, look at the top face over here. Look at the top face. This is the center of top face. I'm keeping the particle there, right? Similarly, look at this particular face, bottom face at the center of it, side face at the center of it, at the center of it, front face center, back side face. I'm keeping it here as well. So, do you see this particular cube in which the constituent particles, they are present at corners as well as face center? Whenever you see such kind of the cube, such kind of the unit cell, in which the constituent particles are present at the corners and at the face centers, you'll be calling this particular unit cell as face-centered cubic units. You'll be calling it as face-centered cubic units, right? Now, my dear students, if I ask you about this particular corner particle, is this corner particle completely inside the cube? No. Only its 1/8 part is inside the cube. So I must say, its contribution towards the unit cell is 1/8. Okay? Now look at this center particle, face center particle. Is this face-centered particle completely inside the cube? Is this face-centered particle completely inside the cube? The answer is a big no. Why is that? Because on one side of it, on this particular side of it, there will be one more cube. There will be one more cube, right? There will be one more cube like this. Or let me represent it. Let me show you this particular particle. Let's talk about this particular particle. Right here, I do not have space. I've written something here. Or let's write it here only. Let's write it here only. See, talk about this particular particle. So there is one cube. On this particular side, there will be one more cube whose top surface will be this one. Whose bottom surface will be this one. Right? Perfect. So I would say half of the particle lies in this cube and half of the same particle lies in this cube. So you can clearly say contribution of this face-centered particle towards the cubic unit cell, that is 1/2, which I have mentioned over. Contribution of corner particle 1/8, face-centered particle 1/2. Are these things clear to everyone? Quickly let me know in the chats. Yeah? Quickly let me know in the chats if all the things are clear till here. Quickly. Then only I can move ahead. This was just the quick idea. This was just the quick idea about different types of unit cells, right? Which we have to discuss in this chapter. There are a few more, we'll discuss them as well. Now, dear students, one thing I've mentioned over here as phase diagonal particles, they touch each other. Now, what is a phase diagonal? What is a phase diagonal? What exactly you need to do? Take one of the face. Let's say I'm talking about this top face. Let's say I'm talking about this top face, okay? So if you join this particular corner with this particular corner, you'll be calling it as one phase diagonal. Similarly, if you join these two, you can call this as phase diagonal as well. Let's say I'm joining these two. So this is the phase diagonal over here. So if I ask you which all particles lie along this phase diagonal, it is this particle, the one here, and the one here. These are the three particles which lie along this phase diagonal. And all the particles which lie along the phase diagonal, they'll be touching each other. Right? So I would say this one will be touching this one. So let me represent it to you. So this particular particle, the one over here, and the one over here, they'll be touching each other. I hope this is clear to everyone. Okay? Perfect. Perfectly done, guys. Is it clear? Wonderful. So this was just the quick overview of different types of unit cells. Now, let's exactly do the analysis of the unit. Let's properly understand these unit cells in detail. Okay? So I'm marking the heading as analysis of unit cells. Analysis of unit cells. And the first unit cell which we are going to analyze here, that is going to be your simple cubic unit cell. Simple cubic unit cell, which you represent with SCC. Let's try to analyze this particular unit cell. Okay. Now already we have discussed few important points about SCC, right? So what was that? We know in case of SCC, the constituent particles, they're only present at the corners. Let's say I'm making a cube over here. Let's say this is the cube. And what exactly I'm doing? I'm going to keep the constituent particles only at the corners. Only at the corners. Okay. So should I be calling this particular unit cell as simple cubic unit cell? Absolutely. Right. Now, dear students, the first point which we are going to discuss about this simple cubic unit cell. What is that? That's what you call as effective number of particles. Effective number of particles. This is the first point which we have to discuss. Or effective number of particles, you call it as the rank of the unit cell as well. You call it as the rank of the unit cell as well. And let me tell you, this effective number of particles, the rank of the unit cell, it is represented by Z. It is represented by Z. Now, the point is, how do we calculate the rank of the unit cell? First, I'll show you how to calculate, and then I'll make you understand what it means. First, I'll show you how to calculate this Z. Effective number of particles Z. In case of simple cubic unit cell, the constituent particles are only present at the corners. The contribution of the corner particle towards the unit cell, that's 1/8. How many corner particles do we have? In total, we have got 8 corner particles. So the value comes out to be 1. So I'm writing 1 particle per unit cell. 1 particle per unit cell. What exactly it means? As I told you already, look at this particular particle. It's not completely inside the cube. It's 1/8 part only is inside the cube. It's 1/8 part only is inside the cube. It's 1/8 part is only inside the cube, right? All the corner particles, right? Only their 1/8 part inside. Only their 1/8 part is inside the cube, right? So 1/8 of this, 1/8 of this, 1/8 of this, 1/8 of this, 1/8 of all the 8 particles, 1/8 of 8, all the 8 particles comes out to be 1. So effectively, there is 1 particle inside this unit, right? Perfect. Yeah, is it clear to everyone? Quickly, people. This is the first point. Effectively, it is 1 particle only. Yeah. I hope it's clear to everyone. Or let me make you understand it like this as well. If you have any doubts in understanding this, let me make you understand this in a simpler way. For example, this is a cube. For example, this is a cube, right? Perfect, this is a cube. In case of simple cubic unit cell, imagine that hypothetical situation I'm creating. Imagine that you enter inside this cube. Imagine that you are here. Imagine that you are at the center of the cube. Now you are looking at this particular corner. Will you be able to see this whole corner particle? No. Only 1/8 part you can see. Similarly, only 1/8 part you can see. 1/8 part you can see. 1/8 of every corner particle you can see when you keep yourself here at the center, right? Now imagine that I'm giving you one empty cube and I want you guys to make sure that this empty cube looks like SCC, looks like simple cubic unit cell. What you'll be doing, you'll be taking 1 particle. You'll be dividing it into 8 equal parts. After dividing this particle into 8 equal parts, you'll be taking 1 part of it. And this particular part which you took, you'll be fixing it here, right? Similarly, 1 more part, you'll be fixing it here. 1 more part, you'll be fixing it here, right? At every corner, you're fixing 1/8 part. Now, if I say, enter into this cube and look at the corners, you're still going to see 1/8 part only. You're still going to see 1/8 part only, 1/8 part only. So can I say 1 particle is enough to make 1 simple cubic unit cell? I hope now it's clear, right? 1 particle is enough to make a simple cubic unit cell. So effectively, there is only 1 particle of which simple cubic unit cell is made up of. Okay? This was point number 1. Talking about the second point. The second point related to simple cubic unit cell. What is that? That is the relation between A and R. What is A and what is R? Let's have a look. Relation between A and R. So my dear students, for example, this is your simple cubic unit cell, right? It's a cube in which the constituent particles are only present at the corners, right? This is your simple cubic unit cell. Now, first of all, the edge length of this particular cube, the distance from here to here, I'm representing it with A. A stands for edge length of the cube. At the same time, if I select one of the particle, let's say 1 particle I've selected, I'm assuming that its radius is R. Now, I've told you already, in case of SCC, the adjacent corner particles, they touch each other. So first of all, this particular particle and this particular particle, should I be calling them as the adjacent corner particles? Absolutely, they are the adjacent corner particles. So they must be touching each other. So let me show it to you. This is this particular particle and the one which is here, it would look like this. Okay. Now you tell me, what is the distance from center till the circumference? It's R. What is the distance from center till circumference? It's R. So can I say this whole length is called as A? When you want to write A in terms of R, it's going to be R plus R, which makes it 2R, right? So I can say the relation, the simplest relation between A and R is equal. A is equal to R. A is equal to R. Or you can say R is equal to A by 2. R is equal to A by 2. This is one more parameter which you need to remember about SCC. One more important parameter, right? A stands for edge length of the cube. R stands for the radius of the particle. Now, my dear students, the third point, which is very, very, very important. What is that? That's something called as packing fraction. or let me calculate packing efficiency. Packing efficiency of the unit cell. The point is, what is packing efficiency of the unit cell all about? What is packing efficiency of the unit cell all about? Before making you understand what this packing efficiency exactly is, let me show you how to calculate the packing efficiency. Before making you understand what this packing efficiency is, let me show you how to calculate it first. Okay? And packing efficiency I'll be calculating with the help of one result. Volume of constituent particles inside the unit cell divided by volume of the unit cell multiplied by 100. So first of all, what exactly I'm doing? I'm trying to calculate packing efficiency, which is equal to volume of constituent particles inside the unit cell. My dear students, right now, I want to calculate the packing efficiency of SCC. And in case of SCC, the particles are only present at the corners. So first of all, if I ask you whether this particular particle, is it completely inside the cube? No. Only its 1/8 part is inside the cube. Okay? Let's assume that volume of this whole particle, for example, that's 4/3 pi r cube. Volume of this whole particle, that's 4/3 pi r cube. Okay? Can you let me know what volume of this particular particle, is inside the cube? You'll say 4/3 pi r cube, that is the volume of one whole particle. I'll be multiplying it with 1/8. So what is 1/8? I mean, what is this term? What is this particular term? What is this particular term? This is the volume of the corner particle that lies inside the cube. This is that volume of the corner particle that lies inside the cube. How many such kind of corner particles we have? We have 8 corner particles like. Okay. So if I ask you what is the meaning of this whole term now, I got that volume of all the corner particles which lies inside the cube divided by volume of the unit cell. Unit cell is cubical in shape, right? And the edge length of the cube is A. So volume of the cube, volume of the unit cell is cubical in shape. So it's going to be volume of cube. Volume of cube is A cube. Multiplied by what? Multiplied by 100. Perfect. Simple. Now, dear students, we know already A is equal to 2R. So instead of A over here, instead of A cube over here, I can write 2R ka cube. Perfect. I can write 2R ka cube. Now this R cube gets cancelled out. When you put exactly the value of pi as 3.14 and solve it, you'll be getting the value as 0.524 multiplied by this particular 100. Okay. And the final value comes out to be 52.4%. So if I ask you what this 52.4% is all about, this is something which you call as packing efficiency. This is the packing efficiency of SCC. Now what that means? My dear students, it means that out of the total volume of the cube, 52.4% volume will be covered by the constituent. Out of the total volume of the cube, 52.4% volume is covered by the constituent particle. Right? Okay, out of the total volume of the cube, 52.4% volume is covered by the constituent particle. What about the remaining volume? What about the remaining space? See, it's simple. Out of the total space available inside the cube, 52.4% space is covered by the constituent particle. The remaining space will be empty. And empty space is something which you call as voids. So if you ask me, what about the percentage of voids? What about the percentage of voids in SCC? It's going to be 100 minus this term, which comes out to be 47.6%. So this much space, this much volume of the cube will remain empty. Right? Perfect. Is this clear to everyone? So 52.4% volume of the cube is covered by the constituent particles, and the remaining 47.6% volume is going to remain empty, and that empty space is something which you call as voids, right? So percentage of voids in SCC, that's equal to 47.6. I hope it's super clear to you. Yeah. Perfect. And my dear students, if you just have a look on this particular term, 0.524, only this particular term, this is something which you call as packing fraction. This is something which you call as packing fraction. This 0.524, this packing fraction, this is packing efficiency. So I hope you got to know what kind of idea this packing efficiency gives us. Okay. This was the third point about the SCC. Now talking about the fourth point. The fourth point is coordination number. How do we define the term coordination number? First of all, how do we define the term coordination? Coordination number is simply defined as the number of nearest, or you can say immediate neighbors. The number of nearest or immediate neighbors which a particle has comma equidistant from it. Equidistant from it. So what it means exactly? Let's see. What it means? Let's see. First of all, let me make you understand what this coordination number is. Then we'll talk about the coordination number in case of SCC. That's a separate debate. Okay, let me make you understand what this means. For example, imagine that this is Na positive over here, right? I'm drawing a circle over here. Perfect. Na positive is present in the center, right? This is one more circle over here. This is, for example, one more circle. These are three concentric circles. Perfect. I'm keeping a Cl negative here. I'm keeping a Cl negative here. I'm keeping a Cl negative here. And I'm keeping a Cl negative here. Can you let me know how many neighbors this Na positive has? It has 4 neighbors. It has 4 neighbors, right? 1, 2, 3, 4. All the 4 neighbors are equidistant from it. So I'll say the coordination number of this Na positive right now is 4. Okay? The coordination number of this Na positive right now in this current scenario, that's 4. But if I keep one Cl negative here and one Cl negative here, now if I ask you how many neighbors this Na positive has, right now it has got 6 neighbors. Right now it has got 6 neighbors. But now if I ask you how many closest neighbors it has, now it has got 2 closest neighbors, which are equidistant from it. So the number of nearest neighbors, the number of closest neighbors which a particle has, equidistant from it, that defines its coordination number. So coordination number of this Na positive is 2. Coordination number of this Na positive right now is 2. Now, for example, I'm keeping one Cl negative here. Now I'm asking you to calculate the coordination number. How much it's going to be? There's only one nearest neighbor. There's only one closest neighbor. Okay. So right now the coordination number of this Na positive is 1. Perfect. Now, I hope you got the idea of what coordination number is. If you just got the idea of what coordination number is, let's try to get the coordination number of a particle in case of SCC, in case of simple cubic unit. Okay. So let me make one simple cubic unit cell over here so that you can visualize the coordination number properly. First of all, in case of simple cubic unit cell, we know the constituent particles, they are present only at the corners of the cube. Okay. For example, I'm selecting, let's say I'm selecting this particular particle. I need to calculate its coordination number. Right? What that means? I need to know how many nearest neighbors it has, how many immediate neighbors it has, which are equidistant from it. Perfect. Already I've told you one important thing. In case of SCC, which all particles touch each other? In case of SCC, adjacent corner particles touch each other, right? So can I say this particle and this particle, they are adjacent corner particles, they'll be touching each other. Perfect. If they are touching each other, that means these two are nearest neighbors only, right? Its nearest neighbor has to be this one. Do you agree with this? Right? I'm talking about this particular particle. Its nearest neighbor has to be this one because this one is touching this one. Perfect. Similarly, my dear students, this is one nearest neighbor which it has because this white colored particle is touching the yellow colored particle. Similarly, my dear students, do I call these two as adjacent corner particles? Absolutely. They'll be also touching, right? They'll be also touching. These two are also the adjacent corner particles. So these two particles will be also touching each other. Correct? Now, on the side of this particular cube, there is one more cube whose top surface is this one. Okay? And if this is SCC, that means this cube which is aside of it, that should also be SCC. The particles should also be present at the corners, right? So look at this particular particle. These two I'll be calling as adjacent corner particle. Okay, so they should be touching as well. Now the cube which is just behind this particular cube, whose top surface is this one, right? Let me call this particular particle. These two are also adjacent corner particles. Perfect. Now similarly, there'll be few more cubes at the top. One of the surface I'm going to show over here, right? Let's keep the particle here. So this one and this one, they're also the adjacent corner particle. Now I'm asking you, how many adjacent corner particles are touching this particular particle simultaneously? 6, right? So if I ask you how many nearest neighbors, if 6 particles are touching this particle simultaneously, so its nearest neighbors are 6. So its nearest neighbors are 6, right? And the number of nearest neighbors which a particle has, which are equidistant from it, that defines its coordination number. So coordination number of this particular particle over here, it's going to be 6. So do remember from now on, what's the coordination number of each particle? In case of SCC, that's going to be 6. Is this clear? Is this clear to everyone? Perfectly done. Yeah, perfectly done. So these were the 4 points which are really very important as far as your SCC is concerned. Point number 1, rank of the unit cell is 1. Effective number of particles in SCC, that's 1. A is equal to 2R. Packing efficiency is 52.4%. Wide percentage is 47.6%. Coordination number of each particle in the unit cell, that's 6. Okay, perfect. Is it clear? All the things are clear to you? All the things are clear to you. Say yes or no in the chats. Quickly. Say yes or no in the chats. Quickly. Let's try to analyze the body-centered cubic unit cell. First, tell me in the chats whether all the things are clear. Body-centered cubic unit cell. Time to analyze this particular unit cell. Quickly in the chats. All the things are clear? Yes? Wonderful. So my dear students, body-centered cubic unit cell already we have discussed a bit. Like in case of body-centered cubic unit cell, the particles are present at the corners and at the body center. That was point number 1. Point number 2 was the body diagonal particles, they touch each other in case of BCC. So these 2 things already I have mentioned, right? So let's try to analyze this BCC now. So the first point about BCC, what is that? That is effective number of particles. That is effective number of particles, which you call as the rank of the unit cell as well. And how do I represent it? I represent it by Z. Okay. So how do I calculate Z for BCC? In case of BCC, the particles are present at the corners and at the body center. The contribution of the corner particle is 1/8. There are 8 corner particles like that. The contribution of body centered particle is 1. There is only 1 such particle in case of BCC, right? So the value comes out to be 2. So you'll be writing 2 particles per unit cell. 2 particles per unit cell. So this is something which you call as rank of the unit cell, or you can call it as the effective number of particles. I hope this is clear. The second point that's important, what is that? That is the relation between A and R. How do we exactly get the relation between A and R? How do we get the relation between A and R? Let's try to get the relation between A and R in case of BCC. So first of all, I'm going to make one BCC over here so that you can analyze it properly. Okay, it's clear imagination here, nothing else. It's clear imagination over here, nothing else, right? So first of all, I'm keeping the constituent particles at the corners, and apart from the corners, I'm keeping 1 particle at the center of the cube. So this is one clear-cut BCC over here. Yeah. Now people, the relation between A and R, right? So first thing, let's say that edge length over here of this particular cube is A, right? Let's assume that, number 1. Number 2, radius of each particle is R. Let's assume that radius of each particle is R. Perfect. So over here, I'll be using some geometry. One simple geometry I'm using. Okay. Since you must be knowing For example, you have got a right angle triangle. There's a right angle triangle. Let's say this side is A, this side is A. So hypotenuse has to be root 2A. This everyone must be knowing, right? Let's say I've got a right angle triangle like this. This is A. This is root 2A. That means hypotenuse has to be root of 3A. This is something which is completely basic, which you all must be, right? Yeah. Now guys, have a look. For example, I'm talking about one triangle over here. This is the triangle I'm talking about. This is the triangle I'm talking about, right? The distance from here till here, it's A. The distance from here to here, it's A. Now, what about this hypotenuse distance? Hypotenuse distance has to be root 2A, correct? So, let me call this as point A, let me call this as point C, let me call this as ABC, right? So, what about AC length first of all? AC length has to be root of 2A. Point number 1. AC length has to be root of 2A. Now, my dear students, analyze and understand few things. AC length is root of 2A. Now, for example, if I select this particular edge, this is the edge I'm selecting. This particular AC, I'm selecting. And these two, I'm selecting as well. I'm joining them. Let me call this as A, this is C, and this is D. We got a triangle ACD. In the triangle ACD, if you talk about AD length, that's the edge length, that's A. AD length is A. If you talk about AC length, that is root of 2A. If I talk about CD length, what the CD length is going to be? CD length. So this is A, this is root 2A, so CD length has to be root of 3A, right? CD length has to be root of 3A. Now, dear students, this CD length is something which I call as body diagonal. If you see it carefully, it's a body diagonal basically. It's a body diagonal. And we know, in case of BCC, body diagonal particles, they touch each other. So, this particular particle, this one and this one, they should be touching each other, right? They should be touching each other. So, this particle, the one here and the one here, they should be touching each other. So, how exactly they should be touching each other? How exactly they'll be touching each other? Have a look. So, this particular particle, let me make it like this. The other one, like this. The one over here, simply like this. Okay? So, I'm talking about the CD length. I'm talking about the distance from here till here, right? We already know it's root of 3A, but I want to write it in terms of R. Can I say the distance from here till this circumference? It is the radius of this particle, right? The distance from here till here, it is the diameter of middle particle. The distance from here till here, it is the radius of this particular particle. So can I say this CD length, which is basically root of 3A, that's equal to R plus R plus R plus R. So that comes out to be 4R. So I can categorically say root of 3A is equal to 4R in case of BCC, right? That's something which you need to remember, nothing else. Root of 3A is equal to 4R. Or you can say R is equal to root 3A divided by 4. R is equal to root 3A divided by 4. This is the relation between A and R in case of BCC. I hope it's clear. In case of SCC, it was R is equal to A by 2. And over here, it's equal to R is equal to root 3A by 4. Nothing else. Perfect. Is it clear? Is it clear to everyone? Quickly. Quickly, guys. It should be. Okay. So this was the second point about BCC. Talking about the third point. What is our third point? That is packing efficiency. That is packing efficiency. So first of all, how do we get the packing efficiency? Packing efficiency is calculated as volume of constituent particles inside the cube. I already told you that. Divided by volume of the unit cell multiplied by 100. Now, dear students, let's try to calculate the packing efficiency of your BCC. So again, what I'm doing is I'm going to make a cube over here. This is the cube which I've made. In this particular cube, I'm keeping the constituent particles at the corners and at the body center. So this is one BCC over here, right? This is one BCC over here. Now, my dear students, just tell me one thing. How do we get the packing efficiency? Volume of constituent particles inside the cube. Is this particle completely inside the cube? No. Only 1/8 part is inside. Let's assume that volume of this whole particle is 4 by 3 pi r cube. Volume of this whole particle is 4 by 3 pi r cube. Okay, volume of the whole particle, that's 4 by 3 pi r cube. Can you let me know what volume of this particular particle is inside the cube? I'll say 1 by 8 multiplied by 4 by 3 pi r cube. What is this particular term? It is that volume of the corner particle. That volume of the corner particle that lies inside the cube. We have got 8 such kind of corner particles. So what about this whole term? It is that volume of all the corner particles which lies inside the cube. Apart from the corner particle, we have got this particular particle as well, which is at the center. And it's completely inside the cube. So I'll have to count its entire volume. Perfect. So what do I call this whole term? This whole term which I have kept in brackets, what is it? This is the volume of all the constituent particles which lie inside the cube, right? Divided by volume of the unit cell. The unit cell is cubical in shape. The edge length is A. And volume of cube, that's A cube. Multiplied by what? Multiplied by 100. Nowadays, students, already you know what is A in terms of R. Few minutes back, we got the relation. R is equal to root 3 by 4. So A is equal to 4R by root 3. A is equal to 4R by root 3. So it is A cube. So 4R divided by root 3 ka cube. Perfect. So R cube, R cube, R cube everywhere gets cancelled out. When you solve it, when you put all the values of pi, etc., you'll be getting the exact value as 0.68 multiplied by this particular 100, which comes out to be 68%. This 0.68 over here, you'll be calling it as packing fraction, and this 68%, you'll be calling it as packing efficiency, right? Now, I want you guys to tell me, what is the meaning of this 68%? It means out of the total volume of the cube, 68% volume is occupied by the particle. Out of the total volume of the cube, 68% volume is occupied by the particle. So the remaining volume, that will be empty. And empty space is something which we call as voids, right? So if this is the packing efficiency, if I ask you, what about the percentage of voids? What about the percentage of voids? That has to be 32%, right? So this much percentage of space of this particular cube is going to remain empty. I hope it's clear. So let me know quickly in the chats if all these things are clear. Yeah? Quickly. Okay. So this was the third point about BCC. Now, let's have a look on one more point. What is the fourth point of BCC? The fourth point is coordination number. Coordination number in case of BCC, right? Okay. So, again, I need to draw one BCC over here, or if there was a space here. Okay, let's talk about here only. Let's talk about this one only. See, if you talk about this particular particle, you want to calculate its coordination number. Okay. My dear students, all the corner particles will be touching it. All the corner particles, they'll be touching it. All the corner particles will be touching it. Okay. Why is that? Have a look. First of all, if you select this particle and this particle, you join them, it's going to be a body diagonal. All the particles along the body diagonal, they'll be touching. So this particle will be touching this and this will be touching this. So these three will be touching. So basically, in this particular line, if you talk about this one, two particles will be touching this particle. One is this, one is this. Okay, two. Similarly, if you join this one with this one, it's going to be one more body diagonal, right? So similarly, in a cube, you can draw four body diagonals. Along one body diagonal, two particles will be touching this one. And since you can draw four body diagonals, so 4 2s comes out to be 8. Okay? 4 2s comes out to be 8. So 8 particles are touching this particular particle simultaneously. So its coordination number has to be. Right? Perfect. Very simple and basic. I hope you got what I said. Imagine it like this. First of all, we have got the body-centered particle here, for example. if I'm joining this particular corner, with this particular corner, if I'm joining these two, it's going to be a body diagonal, right? Towards the body diagonal, particles touch, right? So this particular particle at the center, its two touching particles will be this one and this one. Number one. Number two, if you join this particular corner with this particular corner, it's going to be one more body diagonal. So three particles will be touching. This one, and this one, right? Similarly, for example, if you are joining this particular particle with which one? Can you let me know with which one? With this one. It's going to be one more body diagonal. So three particles again are touching. If you join this one and this one more body diagonal. So again, these three particles will be touching. So if I talk about the particle at the center, towards this particle, 8 corner particles are touching, and the number of particles touching a particular particle simultaneously, that defines its coordination, right? Yeah? Perfect. So do remember, in case of your BCC, the coordination number of each particle is 8. Similarly, if you talk about this one, its coordination number will be 8. Its coordination number will be 8. Perfect. When you have to calculate the coordination of the body-centered one, you'll be counting the corners. You'll be counting the corner particle. When you have to calculate the coordination number of the corner particle here, you'll be calculating the body center. This is one body center. The other body center will be here. Similarly, there are in total 8 cubes. So 8 body-centered particles. So 8 nearest neighbors for this one. So in short, remember, in case of your BCC, the coordination number of each particle is 8. Final conclusion, which is important. Okay. Now one unit cell is left. What is that? That is your face-centered cubic unit cell. That is your face-centered cubic unit cell. And this face-centered cubic unit cell, you represent it with FCC. You represent it with FCC. Now let's try to analyze the FCC in detail. All the things related to FCC, the main things related to FCC, I've already given you. Okay. Now let's try to analyze it in detail. First of all, let's try to make one FCC over here. Let's see if you can do all the things properly or not. My dear students, this is a cube. This is a cube over here. Okay. And I'm going to keep the constituent particles at every corner. And apart from the corners, I'm going to keep the constituent particles at the center of each face. Center of each face. Center of front face, center of back face, right? So this is your face-centered cubic unit cell. It is your face-centered cubic unit cell. My dear students, in this face-centered cubic unit cell, since the particles are present at the corners and the face centers, the first point which we are going to calculate, that is effective number of particles. Effective number of particles, which is represented by Z. So how do you calculate the effective number of particles? Can you give it a try? See, first of all, in order to get the value of Z, the particles are first of all present at the corners. Corner contribution is 1/8. There are total 8 corner particles. Apart from that, the contribution of face-centered particle is 1/2. And in total, there are 6 face-centered particles. There are total 6 face-centered particles over here. When you solve it, you'll be getting the value over here as 4. I'm writing 4 particles per unit cell in case of FCC. So effectively, there are 4 particles in case of FCC, right? The rank of the FCC is going to be 4. Point number 2. What is that? That is the relation between A and R. The relation between A and R. Relation between edge length and the radius. How do we get it? See, people. Since first of all, this particular length is something which you call as edge length, which is represented by A, right? And in case of FCC, I've told you, face diagonal particles touch. Face diagonal particles touch, right? So if you select the top face, just select the top face and join these two. So it's a face diagonal. It's a face diagonal. Now, my dear students, let me mark a triangle over here. Let me mark a right angle triangle over here. Calling this as A, calling this as B, and calling this as C. Okay, this is a right angle triangle ABC. So first of all, AB length, that has to be A because that's edge length. BC length is again A, so AC length has to be root of 2A. So this is understood, right? AC length is nothing, it is root of 2A. AC length is root of 2A. Now what is AC basically? AC is the face diagonal. AC is the face diagonal. And I have told you in case of FCC, face diagonal particles, they touch each other, right? So this one, and this one, they'll be touching each other. Let me show it to you. This is one particle. This is one more here. And this is one more here. So these three particles are touching. So if I talk about AC length, AC, now check this complete AC length, which is equal to root of 2A, right, in terms of R. So the distance from here to here, it's R. From here to here, it's again R. From here to here, it's R. From here to here, it's R. So basically, it's going to be root of 2A is equal to 4R, right? Or you can say R is equal to A divided by 2 root 2. So this is basically the relation between A and R in case of what? This is the relation between A and R in case of F. This is again one more point which you need to remember. Okay? Again, one more important point which you need to remember. That is the relation between A and R in case of FCC. Right? So R is equal to A divided by 2 root 2 in case of FCC. The third point related to FCC, what is that going to be? That's again going to be, you know it. That's going to be packing efficiency. Calculate the packing efficiency in case of what? In case of FCC. How do we get the packing efficiency? Volume of constituent particles inside the cube. Now, dear students, in case of FCC, how many particles we have? We have two types of particles. Corner particles and face center particles. Corner particles and face center particles. If I ask you about this particular particle, is this wholly and solely inside the cube? No. Only its 1/8 part is inside the cube. Yeah. If the volume of this whole particle is 4/3 pi r cube, so what volume of this particular particle lies inside the cube? It's going to be 1/8 multiplied by 4/3 pi r cube. What is this term? What is this whole term? It is that volume of the corner particle, that volume of one corner particle that lies inside the cube. How many such kind of corner particles we have? 8. Apart from corner particles, what do we have? Face-centered particles as well. What volume of face-centered particle is inside the cube? It's 1/2 into 4/3 pi r cube. 1/2 into 4/3 pi r cube. It is that volume of the face-centered particle which lies inside the cube. How many such kind of face-centered particles we have? 6. If I ask you, what about this whole term? What about this whole term? What does it give me? It gives me that volume of all the constituent particles. That volume of all the constituent particles which lies inside the cube in case of what? In case of FCC. Right? Divided by volume of the unit cell. Unit cell is cubical in shape and volume of cube is A cube multiplied by 100. So dear students, already I told you, instead of A, you guys are going to write 2 root 2r. So instead of A, it's going to be 2 root 2 r ka cube. Now, it's a matter of calculation. R cube, everywhere cancelled out, right? Put the value of pi, etc. So you'll be getting the packing efficiency over here as, you'll be getting it as 0.74. And at the end, multiply it with 100. So the value comes out to be 74%. So dear students, this 0.74, you'll be calling it as packing fraction. And this 74%, you'll be calling it as packing efficiency. Now, you are going to tell me what is meant by this 74%. Quickly. What is meant by it? I can say, out of the total volume of the cube, 74% volume is covered by the constituent particle. Right? Out of the total volume of the cube in FCC, 74% volume is covered by the constituent particle. And the remaining volume, which is going to be 26%, that's going to be empty space. And empty space is something which you call as voids. Right? So if I ask you, what about the percentage of voids in FCC? It's just going to be 26%. I hope it's clear. Yeah? I hope it's clear. Now, the fourth parameter. What is the fourth parameter in FCC? That is coordination number. Guys, over here you have to imagine things. Over here you have to imagine properly. Coordination number. Coordination number in case of FCC. This is something which you have to imagine. Otherwise, you won't get it. Okay? See, guys. So first of all, I'm going to make a cube over here. You need to imagine it properly, okay? I'm going to make a FCC in which the particles are present at the corners and at the face center. This is the center of front face and this is the center of back face. Okay, this is one FCC. We know in case of FCC, which particles touch. In case of FCC, face diagonal particles. Right? For example, I want to calculate the coordination number of this particular particle. The coordination of this particular particle. So I'll count all the particles which are touching this particular particle. I'll count all those particles which must be touching this particular particle. That gives me the coordination number. Now give it a try. See guys. For example, if you talk about this top face, let's talk about top face. If you join these two, it's going to be a phase diagonal. And all the particles along a phase diagonal, they'll be touching each other, right? That means this particular particle will be touching this particular particle. Number one. Number two, on the side of it, there'll be one more cube whose top surface is this one. Whose top surface is this one. There will be one particle at the center of this face as well. Because if this is face-centered cubic unison, on the side of it, there'll be one more face-centered cubic unison. Now people, if you join these, it's going to be a phase diagonal, right? It's going to be a phase diagonal. So this one and this one, they're also touching each other. Perfect, right? Similarly, there will be one cube which will be just behind this one, whose top surface is this one. At the center of it, there is one more face center here. And if you join this, it's going to be a phase diagonal. And along the phase diagonal, all the particles touch. So this one will be touching this one. At the same time, there'll be one more cube whose top surface is this one. This is the face center. Join them. It's going to be phase diagonal, right? So this particle will be touching this one. So if you talk about this particular plane, in this particular plane, how many particles are touching this yellow colored particle? 4 particles are touching this yellow colored particle in this plane over here, right? In this plane. Now look at the other particles. Imagine it carefully. Imagine it carefully and properly at the same time. Okay. So dear students, if you talk about this particular face, just talk about this particular face. Just draw a line from here to here. It's going to be a phase diagonal. All the particles along a phase diagonal, they'll be touching, right? So I would say this particular particle will be touching this particular particle. Okay. Perfect. Similarly, can I say this is one more face which will be here? At the center of it, there'll be one more particle. Since this is a phase diagonal, so this one and this one, they'll be also touching. Similarly, there'll be 2 faces on the top as well. Similar faces on the top as well. Perfect. So one here at this face center, one here at this face center. So this is also a phase diagonal. So this one and this one will be touching. This is also a phase diagonal. So this one and this one will be touching. So in this vertical plane, how many more particles are touching? In this vertical plane, I must say 4 more particles are touching this yellow colored particle. So 4 and 4 comes out to be 8. Now, which particles are left? See guys, understand. For example, if I talk about this particular face, imagine carefully. If I talk about this particular face, yeah, this is its face center. This is its face center particle. If you join this and this, it's going to be a phase diagonal. And all the particles lying along the phase diagonal, they should be touching. So this one and this one, they are touching. Similarly, on this side, there will be one more similar sort of face. This is one more similar type of face, right? At its center, there will be a particle. Join them. It's going to be a phase diagonal. So this one and this one touching. Similarly, at the top, there is one more similar face. There is one more similar face. At the center of it, there is a particle, right? Face-centered particle. Join them. It's going to be a join them. So this particle and this particle, they should be touching as well. Similarly, there'll be one more similar sort of face over here. And one particle will be present at the center of this particular face. So if you join them, it's going to be a phase diagonal. So this one and this one will be also touching. Now you guys are going to tell me how many particles are touching this yellow colored particle simultaneously. So 12. The number of particles touching a particular particle simultaneously, that defines its coordination. So coordination number, do remember, of each particle in case of FCC, that has. Clear? 4 in one plane, 4 in one more plane, 4 in one more plane. Yeah? Say yes or no in the chats, quickly. Say yes or no in the chats, quickly, everyone. I hope it's super clear to everyone. Yeah? So 12 particles are touching this particular particle simultaneously. That defines its coordination. So my dear students, since till now we have done the analysis of the 3 unit cells. One is SCC, one is BCC, and one is FCC. Okay? Someone is asking, what about the coordination number of the face-centered particle? It will be also 12 only, right? I cannot show it here. In the diagram, it will be messed. So do remember it. Yeah? Perfect. One more thing, guys. Let me quickly summarize all the things which we have discussed till now. Quickly, I'll be summarizing all these things. Okay, quickly, I'm summarizing all the things. So 3 types of unit cells we have discussed, right? One is your SCC, one is BCC, and one is FCC. 3 types of unit cells we have discussed right now. So let me summarize all the things, whatever we have discussed. Okay, so this is SCC here, right? One is SCC, one was your BCC, and one was FCC. Quickly summarizing all the things. From this table, you can get a question. From this table, which I'm going to make, you can get a question. So my dear students, the first point related to SCC, the particles are present only at the corners of the cube. Only at the corners. In case of BCC, the particles are present at the corners and at the body center. And at the body center. In case of FCC, the particles are present at the corners and at the face center. Okay, point number 1. Point number 2. In case of simple cubic unit cell, adjacent corner particles touch each other. Adjacent corner particles touch. In case of BCC, it is body diagonal particles which touch. Body diagonal particles touch. In case of FCC, you can say face diagonal particles. Face diagonal particles, they touch each other. This was the second point, which we have discussed. The third point. Z value for SCC is 1. Z value for BCC, that came out to be 2. Z value for FCC came out to be 4. Okay. A is equal to 2R in case of SCC, right? Or you can write it in terms of R. R is equal to A divided by 2. Over here, R is equal to root 3 A divided by 4. And in this particular scenario, R is equal to A divided by 2. Right? Then we discussed about packing efficiency. Packing efficiency in case of SCC is 52.4%. Packing efficiency here, it is going to be 68%. And here, packing efficiency is equal to 74%. Now, if I talk about the percentage of voids, here it's going to be 47.6%. Percentage of voids here is going to be 32%. And in the last case, percentage of voids is going to be 26%. Right? Then we discussed about the coordination number. Coordination number of each particle here is 6. Coordination number of each particle here is 8. And coordination number of each particle here, it's 12. These are all the parameters which we have discussed about the unit cells, right? Perfect. All clear, guys? All clear? Okay, if I ask you one simple question, see, anything can be asked out of these parameters which I mentioned. Anything can be asked. Anything means anything. These are all questions basically. Yeah? Okay, if I ask you one question, you guys are going to tell me its answer. What is the order of packing in different types of unit cells? Where is the packing efficiency maximum? This was once asked long back. Packing efficiency, where is the maximum? In FCC, it's maximum, followed by BCC, followed by SCC, right? You know it. There is one more unit cell which we are going to discuss afterwards. That's HCP, okay? So HCP and FCC, they have got same packing efficiency. They have got same packing efficiency. HCP and FCC, right? HCP, I'll be letting you know in some time. Is everything clear till here? This is the packing efficiency order. Perfect. Now, dear students, we can solve few questions, right, which can be asked out of the concepts which we discussed till now. So let's see exactly what kind of questions can be asked out of the concepts which we discussed. Have a look. Understand. I'm going to write few questions. Already the questions are written. Already the questions are written in the slides. Let me just find the questions and we'll be solving them. Okay. First of all, before solving the questions, let me just quickly give you the overview of certain things. I told you already what is the contribution of corner particle. Contribution of corner particle towards the cubic unit cell, that's 1/8. How many such kind of corner particles we have? In the cube, we have got 8 corners. Number 1. If I talk about the face-centered particle, contribution of face-centered particle is 1/2. And how many such kind of face-centered particles we have? In a cube, there are 6 face-centered. Okay? Right? Now, dear students, if I talk about the body-centered particle, contribution of the body-centered particle is 1. And in the cube, there is only one body-centered. Done and dusted. Right? Similarly, if I talk about the edge-centered particle, the particle that will be present at the center of the edge, its contribution towards the unit cell is 1/4, and there are 12 edge-centered particles in a cube. There are 12 edge centers in a cube, basically. Okay, so do remember all these things. First part is contribution. Second part is total number of atoms in the cube. Okay, right? Edge center means, let's say, this is one of the face of the cube. Particle is present here. This is the edge-centered particle. This is the edge-centered particle. This one edge-centered, right? Edge-centered, edge-centered. These are edge-centered particles. Their contribution is 1/4. Perfect? Because one edge center is shared by one edge center. It is shared by 4 cubes. For example, if we talk about this particular edge center, it is shared by this cube, it is shared by this cube, and 2 cubes which are present at the top. 2 cubes which are present at the top. So this particular edge, it's shared by 4 cubes. So the particle which will be present here at this center, it will be shared by 4 cubes. So that's why we say the contribution of the edge-centered particle towards the cube, that's 1/4. Yeah? Let's try to solve the questions now. Basic questions. I'm starting with the basic question. You should be solving them on your own. Let me just give you the idea of how to solve. We have got a solid in which 4 types of constituent particles are there. A, B, C, and D. A particles are present at the corners of the cube. B particles are present at the face centers of the cube. C particles are present at the edge centers. D particle is present at the body center. We have to tell the empirical formula of the compound. What is the empirical formula of the compound? Say, A is present at the corner. The contribution of corner is 1/8. There are total 8 corner particles. Right? Done with A. B at face center. The contribution of face center is 1/2. There are 6 face-centered particles. Done with B. Okay. C is at edge center. The contribution of edge-centered particle, 1/4. There are total 12 edge-centered particles. Done and dusted. Contribution of D, body center. Contribution is 1. There is 1 body-centered particle. Now solve it. That's it. 8 it cancel. The value comes out B1. This is 3. This is 3. And this is 1. So the empirical formula has to be A1, B3, C3, D1. So A1, B3, C3, D1. This is the simplest question among all the questions. Okay? Perfectly done. This was question number 1. Let's have a look on the second question. We have got a solid which is made up of 4 different types of constituent particles. A, B, C, and D. 4 different types of constituent particles. A, B, C, and D. A particles are present at 50% of corners. B particles at 75% of face centers. C particles all edge centers. D particles body center. We have to talk about the formula of the compound. My dear students, first of all, what is this 50%? 50% means 1/2. Right? Just let me tell you, 50% is 1/2. If I talk about 25%, 25% is 1 by 4. Okay. 75%, 75% is 3/4. You know it. How to convert percentage into fraction. Now have a look. A particle is present at 50% of corner. 50% means 1 by 2. Multiplied by. Corner contribution is 1/8. In total, there are 8 corners. 8 corner particles. We're done with A. 75%. 75% is 3/4. Face-centered particle contribution is 1 by 2. There are total 6 face-centered particles. All edge centers. Edge center contribution is 1 by 4. There are in total 12 edge centers. Body center contribution is 1. There is 1 body centered particle. Done and dusted, right? Now people, give it a try. 8 get cancelled, the value is 1 by 2. 2, 1, 2, 3. So it's going to be 9 by 4. 4, 1, 4, 3. This is 1. Okay. Now the formula does not mean we do not represent the formula in fraction. So convert it into simplest natural number at least, right? So do one thing. Take the LCM of the denominators here. Take the LCM of denominators. Denominators here are 2, 4, 1, 1. LCM of 2 and 4 is 4. So multiply throughout by 4. Multiply throughout by the LCM of denominators, right? So this value comes out to be 2. This value will be 9. This value will be 12. This value will be 4. So the formula has to be A2, B9, C12, and D4. This is the formula of the compound, which we were supposed to calculate. I hope it is super clear to you. Okay. So moving ahead to one more question. See what kind of different types of questions can be asked. We have got a solid in which we have got 4 different types of particles. A is present at corner, B is present at face center, C at edge center, D at body center. Now the question says, if 2 corner particles and 2 of the face centered particles are removed, if 2 corner particles, you are removing 2 corner particles, and at the same time, you are removing 2 face centered particles as well. After removing 2 corner particles and 2 face centered particles, what will be the formula left? A particles are at corners. Contribution of corner is 1/8. How many corner particles are there in total? 8. Out of 8 corner particles, how many corner particles we are removing? 2 corner particles we are removing. So we'll be left with corner particles. We'll be left with 6 corner particles. Is it clear till here? Just a second, guys. Just a second. Is it clear till here? Quickly. Like all the things are clear till here? Yeah? Is the audio video perfect? Say yes or no in the chats quickly. Perfectly done? Just a second, guys. All right. Okay. B particles are present at face centers, right? What is the contribution of the face-centered particle? The contribution of the face-centered particle towards the unit cell, that's 1 by 2. How many face-centered particles are there in total? 6. Out of 6, how many are you removing? You are removing 2. So we'll be left with 4. We'll be left with 4. So multiply it directly with 4. Yeah? Slowly we are going to increase the level of the equations. C particles are present at the edge centers. Now if I ask you, what is the contribution of the edge-centered particle? Edge-centered particle contribution is 1 by 4. How many edge centers are there in total? 12 edge centers, right? Yeah? Body center. Contribution is 1 and there is 1 body center. Now, just give it a try. It's 6 by 8, which comes out to be 3 by 4. This value is going to be 2. This value is going to be 3. This value is going to be 1. Now, what we are going to do, we are going to take the LCM of denominators. Take the LCM of denominators. What is the LCM of 4 and 1? It's 4. So multiply throughout by 4. This is 4. This is 4. This is 4. Even this is 4, right? So 4, 4 gets cancelled. The value comes out to be 3. So this has to be 8. This has to be 12. this has to be 4. So what should be the formula of this particular compound? It has to be A3, B8, C12, D4. So this is going to be A3, B8, C12, and D4. This is going to be the formula of the compound which we were supposed to calculate. I hope it's super clear to everyone. Yeah? Let's exactly see what are the upcoming questions, right? Slowly we are going to increase the level of the questions. My dear students, look at this particular question carefully. Look at this particular question carefully. The question says, if all the constituent particles along one of the face diagonal are removed, so you are removing all the constituent particles along one of the face diagonal, right? You are removing all the constituent particles along one of the face diagonal. So what will be the formula of the compound then? So first of all, if I select a face, let's say this is the face of the cube, right? Let's assume that this is the top face of the cube, correct? Now, my dear students, for example, I'm joining this particular corner with this particular corner. Let's say I'm joining them. I've joined them, right? Now, along a face diagonal, which all particles do come. I'll say this face diagonal, it passes through two corner particles. Even it passes through the face-centered particle as well, right? So I would say a face diagonal, it passes through two corners and this particular face center as well. The question says, if all the particles along one of the face diagonal are removed. So what does that mean? That means we need to remove two corner particles. We need to remove one face-centered particle as well. Then we have to talk about the formula of this particular compound. Now check it out. Say, A particles are present at the corners. The contribution of the corner particle towards the unit cell, that's 1/8. And how many corner particles do we have? There are in total 8 corner particles, out of which 2 are removed. So I'll be left with 6 corner particles. I hope it's clear. Face-centered particle contribution is 1/2. In total, there are 6 face-centered particles, out of which 1 is removed, right? So I'll be left with 5 face-centered particles. When I talk about the edge-centered particle, the contribution of the edge-centered particle is 1/4. In total, there are 12 edge-centered particles. I'm doing nothing with the edge-centered particle. I'm removing no edge-centered particle over. Right? And if I talk about the body center, its contribution is 1 multiplied by 1. Now give it a try. This is 3/4. This is 5/2. This is 3. And this is 1. Now again, you are supposed to do the same thing. Take the LCM of all the denominators. What is the LCM of 2 and 4? It comes out to be 4 only, right? So multiply throughout with the LCM. That's 4. Multiply throughout with the LCM. Correct? So 4 got cancelled. The value came out to be 3. So 2, 1, 2, 2, 5, 2, 10. B comes out to be 10. So this is going to be 12 and this is going to be 4. So the formula of this particular compound again is going to be A3, B10, C12 and D4. Is this super clear to everyone? Let me know quickly in the chats. Every one of you. Every one of you. Let's slowly increase the level of the question. Oh, this is a nice question. Give it a try. I'm giving you 1 minute time. Give it a try. It's one nice question, guys. Give it a try quickly. Give it a try quickly. It's simple, guys. I'm looking at your chats only. Quickly. All right. So let's see exactly how this sort of question is to be solved. First of all, we have got a particle A which is present at the corners of the cube, B particles at the face center, C at the edge center, and D at the body center. Now the question says, if all the particles along one body diagonal plane, the question is, if all the particles along one body diagonal plane are removed, what will be the formula? Understand. First of all, let me make you clear what exactly the body diagonal plane is and how it looks like. For example, this is the cube. This is one cube over here, right? This is one cube. Let me show you one of the body diagonal planes of the cube. One of the body diagonal planes. I'm talking about this particular edge. I'm selecting this particular edge. Let me just join them. Let me just join them. This plane which we got over here, this is one of the body diagonal planes in the cube. This is one of the body diagonal planes in the cube. Perfect. One of the body diagonal planes. Now, exactly this body diagonal plane, it passes through which all particles? Can you check it out? It passes through which of the particles? Which of the types of the particles? See, this body diagonal plane, it passes through 4 corner particles. Number one, it passes through 4 corner particles. 4 corner particles. Number one. Number two, the body diagonal plane, it passes through body center as well. So one body centered particle as well. Okay. The same body diagonal plane, it passes through these 2 edge centers as well, right? So 2 edge centered particles you need to remove, right? And the same body diagonal plane. Can you have a look? This is the face center of the front face. And this is the face center of the back face, right? So it passes through 2 face centers as well. So if it is mentioned that if all the particles along one body diagonal plane are removed, that means you are going to remove 4 corner particles, 1 body centered particle, 2 edge centered particles, and 2 face centered particles as well. Now, after removing all these particles, what is going to be the formula of the compound? Have a look. A particles are present at the corners. The contribution of corner particle towards the unit cell, that's 1/8. How many corner particles are there in total? 8. Out of 8, how many are we removing? 4. So how many are left? 4 are left. Correct? B is present at the face center. Face center contribution is 1/2. How many face centers are there in total? 6. Out of 6 face centers, how many are we removing? 2. I'll be left with 4. I'll be left with 4 face centers, right? Edge center contribution is 1/4. Correct? How many edge centers are there in total? 12. Out of 12 edge centers, how many we are removing? 2. So we'll be left with 10 edge centered particles. Body center contribution is 1. And there used to be 1, but that one is removed. So I'm left with 0. Perfect. So let's try to solve it. So this 1/2. This will be 2 over here. This will be 5/2. And D is 0. Correct? So just take the LCM. LCM of the denominators is 2. Multiply throughout by 2. Let's see what the value comes exactly. So this value comes out to be 1. This value has to be 4. This value has to be 5. So the formula of this particular compound is going to be A1, B4, C5, and D0. Anyone got this as the result? Anyone got this as the formula? Quickly. Anyone got this as the formula in the question? Quickly, people. Let me know in the chats. Quickly. So I hope all these things are clear till here, right? Now we are going to enter into the new phase of the chapter. That's going to be close packing. Perfect. But before starting the close packing, I think we'll take a break of 15 minutes. Cool? Is 15 minutes enough? Let's take a break for 15 minutes. You guys can have tea or something, yeah? I'll also have. But promise that all of you will join back. Is that a promise? Is that a promise? Quickly, yes or no in the chats? Is that a promise? Quickly. Guys, yes or no? Quickly. Perfect. So let's take a break for 15 minutes. It is 7:05 now. So class resumes at I want every one of you to be back by 7:20. Okay? Surely, Yashwardhan, I'll be doing that. No issues. Guys, be back exactly at 7:20, and you guys can call a lot of your friends as well. Okay? But everyone be back because we have to complete this chapter properly. So guys, are we back? Yeah? Are we all back? Where did I keep the marker? Perfect, perfect, perfect. So, all clear till here? Let me know in the chats quickly. Is every single thing clear till here? Yeah? Say yes or no in the chats quickly, everyone. Perfect. Perfect, guys. So let's solve a few more questions, then we shall move on to something called as close packing, right? Let me see what different types of simple other questions can be asked from the concepts which we have discussed till now, okay? For example, I'm writing one simple question. Let's say the question is lithium forms BCC, okay? Lithium forms BCC with edge length with edge length equal 4 angstroms. Calculate the radius of lithium. These sort of questions can be asked, these basic questions, and see exactly how to deal with them. Dear students, it's mentioned that lithium is forming BCC, right? If lithium is forming BCC, then we know for BCC R is equal to root 3A divided by 4. Perfect. Edge length, which we represent with A, that's given to us as 4. So R will be equal to 4 root 3 divided by 4. So 4 cancel. The value comes out be root 3, and root 3 is approximately 1.7 angstrom. Very simple and basic way, right? So basically, questions based on the formula, the relation between A and R can be asked. Okay? Anything out of this. For example, let me write one more question. The question is like this. An atom X, or let me write it like this, just a second. An element X forms FCC. Radius of X is equal to 2 angstroms. Radius of X is equal to 2 angstroms. Calculate the edge length. Calculate the edge length. Can we solve this? Isn't it again one simple question? Have a look. It's mentioned that X is forming FCC. And in case of FCC, we know R is equal to A divided by 2 root 2. Perfect. What do we have to calculate? Edge length. So A will be equal to simply 2 root 2 multiplied by R. Okay. So 2 root 2 I'm writing as such. R is the radius of X that's given to me as 2. So the final value is equal to 4 root 2 angstroms. And do remember root 2 is nothing. It's approximately 1.4. The value will be 4416, 4145, 5.6 angstroms approximately. This is the edge length of the face-centered cubic units. Isn't it again one simple question? Right? For example, in the same question, you are not supposed to calculate radius. Let's say you are supposed to calculate diameter of the particle. Since you have calculated the radius, so diameter has to be 2 times R. R value already you know. Put it here, get the density. So these sort of basic questions, based on the formula, based on the relation between A and R, they can be asked. Okay? Yeah, simple. Correct? All right, people. Now let's have a look on one more topic, that is close packing. This is important. Close packing. So first of all, let's have a look on something called as close packing in 1D. So first thing, you must be thinking what close packing is all about. My dear students, whenever we talk about close packing, that means we have to arrange the constituent particles in such a way that the empty space between the particles should be minimum. Whenever we talk about close packing, In the close packing, we are going to arrange the particles in such a way that the empty spaces between the particles, they should get minimized. As simple as that. They should get minimized. Okay? The first type of close packing is close packing in 1D. Now, as far as the name is concerned, close packing in 1D. That means we are going to arrange the constituent particles along one of the axes, either x-axis or y-axis or z-axis, in such a way that the vacant spaces between the particles should get minimized. Okay? For example, this is one particle, this is one more particle, one more particle, one more particle. I'll arrange the constituent particles along x-axis, for example, along one of the axes. So should I be calling this as close packing? I won't be calling this as close packing in 1D. I have to make sure that the empty spaces between the particles should get minimized. So if I write it like this, should I be calling this as close packing in 1D now? Yes, I shall be calling this as close packing in 1D, right? Because I've arranged all these particles in such a way that the empty spaces between them got minimized. That too, I've arranged them along one of the axes. So this is close packing in 1D, right? There is nothing in close packing in 1D basically. What we have to discuss, that's close packing in 2D and 3D. Now people, one thing which I would want to understand here. For example, look at this particular particle. Look at this particular particle. Can you let me know how many other particles are touching this simultaneously? How many other particles are touching this particular particle simultaneously? I would say 2 particles are touching this particular particle simultaneously, and the number of particles touching a particular particle simultaneously, that defines its coordination. So whenever from now onwards we'll be talking about close packing in 1D, do remember the coordination number of each particle is going to be 2. Simple. Correct? Is it necessary that we'll do packing only along x-axis? No. You can do packing along y-axis as well. You could have done it like this. No worries at all. This is also close packing in 1 dimension only. You can pack the constituent particles along z-axis. The choice is all yours. Perfect. The actual stuff which we have to discuss, that is close packing in 2 dimension. This is something very important. Close packing in 2 dimension. My dear students, in close packing in 2D, we are going to arrange the particles along 2 of the axes. Or you can say, we are going to arrange the particles along a plane. So let me write one statement over here. When we talk about close packing in 2 dimensions, the constituent particles are arranged along a plane. In such a way that the empty spaces between the constituent particle gets minimized. Okay. Now this close packing in 2D, it's actually of 2 types. Close packing in 2D, it's actually of 2 types, which we have to discuss. One is what you call as AAA packing in 2D. AAA packing in 2D. There is one more that's called as ABAB packing in 2D. So let's try to discuss this AAA packing in 1D first. Okay, let's try to discuss this packing. So my dear students, in close packing in 1D, what was there? In close packing in 1D, we were supposed to arrange the constituent particles along one of the axes. But in close packing in 2D, we are supposed to arrange the constituent particles along 2 of the axes, right? Along a plane. For example, let me make it clear to you. Let's say this is the arrangement which I'm showing. These are the constituent particles, for example. Let me call this particular row of particles, let me call this as row A. This is row A, right? This is row A. Now, my dear students, right now this is close packing in 1D, but I have to do packing in 2D. So I have to keep one more row over here. Now, in order to keep the second row particles, I have got 2 options. Either I'll be placing the second row particles just below the first row particles, or I can place the second row particles in the depressions caused by the first row. But what is the name of the first row? It's row A. What is the name of the second row? It is row A. That means both the rows should be identical. So what does that mean? Both the rows should look same. What does that mean? That means second row particles should be kept exactly down the first row particles. Then only these two rows will look identical. Then only I can call this as row A. The third row is again row A. The third row is again row A only. Perfect. So this is again row A only. Whenever you see this sort of packing, whenever you see this sort of a packing, it is something which we call as AAA packing. And right now, it is the packing in a plane. So it is AAA packing in 2D, right? Nowadays, students, few more things. AAA packing in 2D, few more things. Understand properly what I'm going to say. For example, understand properly what I'm going to say. For example, people, if I join this particular center with this particular center, this one with this one, this one with this one, and this one with this one, I joined the respective centers. After joining the respective centers, what did I get? Can I say I got a square over here? After joining the respective centers of these particles, what did I get? I got a square. Can I say, if I repeat this square along all the axes, if I repeat this square along all the axes, can I say entire crystal will get generated? On repeating this square along all the axes, I must say entire crystal will get generated. So can I simply say something like this? Can I say this square over here, it is the basic structural unit, which upon repeating along all the axes generates the entire crystal. So what do I call this square as? I call this square as the unit cell. So the first point which I would want you guys to remember over here, in case of AAA packing in 2D, the unit cell that gets generated is square in shape. The unit cell that gets generated, that is square in shape. Okay? That's why this AAA packing in 2D is also called as square close packing in 2D. That's why you call it as the square close packing in 2D. Now you must be thinking, what about the coordination number of each particle in this square close packing in 2D? Right? That's something you must be thinking. For example, if I take this particular particle, can you let me know how many other particles are touching this particular particle simultaneously? This one, this one, this one, and this one. So 4 particles are touching one particular particle simultaneously. So its coordination number has to be 4. Right? One more thing. Now you must be thinking, what about the packing efficiency? What about the packing efficiency of this square unit cell over here? What about the packing efficiency of square unit cell? My dear students, since it's a square, right? It's a square. The unit cell is square in shape. How many corner particles do we see? 4 corner particles, right? You have got 4 corner particles over here in this square. How do we calculate packing efficiency? Till now, we used to calculate it with the formula that volume of constituent particles inside the unit cell divided by volume of unit cell. We use the term volume. But over here, we are doing packing in 2D. In 2D, should I be using the term volume or should I be using the term area? In 2D, should I be using the term volume or should I be using the term area? I'll be talking in terms of area now because it's 2-dimensional packing. It is square in shape. For a square, you do not define volume, you define area, right? So the formula becomes area of constituent particle inside the unit cell divided by area of unit cell multiplied by what? Multiplied by 100. So let's calculate it exactly. It has to be equal. Area of constituent particles inside the unit cell. Now people, this is the unit cell. Okay. It has 4 corner particles. Can you let me know whether this particle is entirely inside this square? No. Only 1/4 part of it is inside the square. Similarly, only 1/4 part of this particle is inside the square. right? Only 1/4 part of this particle is inside the square. Only 1/4 part of this particle is inside the square, right? So my dear students, if area of this whole particle is pi r square, can you let me know what area of this particle lies inside the square? It's going to be 1/4 multiplied by pi r square. This is area of one corner particle that is inside the square. How many such kind of particles do we have over here? 4. So I'm multiplying it with 4. Divided by area of this unit cell, area of square. My dear students, if you talk about this square, let me call its edge length. Let's say its edge length, the distance from here to here, edge length, that's equal to A, right? Can I say A will be equal to R plus R, which comes out to be 2R? This distance, the distance from here to here, it's A. A is equal to R plus R, which comes out to be 2R. And area of square, area of unit cell, that side square, which is A square. Instead of A, you can write 2R. So 2R ka square multiplied by 100. R square gets cancelled out, right? When you put the exact values, it comes out to be 28.54%. This is the packing efficiency of the square units. What does it mean? What does it mean? It means that out of the total area of the square, 78.54% area is covered by the particles. The remaining area, that is empty over here. And empty space is something which you call as void, right? So what is the percentage of void here? Percentage of voids over here is going to be 100 minus this thing, which comes out to be 21.46%. So this much area, this much percentage of area of this particular square, that's going to remain empty, right? I hope it's clear to everyone. Perfect, people? So do remember, in case of close packing in 2D, the first type is AAA packing in 2D, in which the unit cell that gets generated, that's square in shape. That's why we call this packing as square close packing in 2D, right? Coordination number of each particle is 4. Packing efficiency 78.54%, right? That means percentage of voids over here will be 21.46%. I hope it's clear to everyone. Yeah. One more thing, guys. One more thing. Just tell me one thing. The unit cell over here is square in shape. If I ask you, what is the value of Z for this unit cell? What is the value of Z for this unit cell? What is the contribution of this particle towards this square? It's 1/4. It's 1/4 multiplied by. How many such kind of particles do we have? 4. So rank of this unit cell is 1. Distance between A and R, relation between A and R is A is equal to R, right? Z is equal to 1. Packing efficiency, everything we got. Coordination number we got. All the things are clear, right? So this was about AAA packing in 2D. Now, dear students, in two-dimensional packing, the second type of packing, that's what we call as ABAB packing. ABAB packing in 2D. What happens over here? What happens in ABAB packing in 2D? Let's try to understand. For example, these are the constituent particles. These are the constituent particles, right? Let me call this particular row as row A. This is row A. The first row is row A. Now look at the second row. Look at the second row. Second row is row B. That means both the rows, first and second, should they be identical? No, they are not supposed to be identical, right? If they were identical, then the name of second row should have been A only. But name of second row is B. That means, does that mean I'm going to place the second row particles just below A? No. I'm going to place the second row particles in the depressions caused by first row. In the depressions caused by first row. I'll place the second row particles in the depressions caused by first row. If this was row A, now this is going to be row B, right? The third row is again row A. What does that mean? That means the third row particles should be just below first row particle. Third row particle should be just below first row particle. Now I'll be calling this as row A again. Perfect. Whenever you see this kind of the packing, you call it as ABAB packing in 2D. Yeah, it's called as ABAB packing in 2D. Now, my dear students, understand one simple thing. This is called as ABAB packing in 2D, right? Now, you guys are going to let me know one thing. For example, locate the center of this particle, this one, this one, this one, this one, and this one, right? Just join them. After joining these centers, what did I get? Can I say I got a two-dimensional hexagon over here? My dear students, if you repeat this hexagon along all the axes, if you repeat this particular hexagon along all the axes, if you repeat it along all the axes, entire crystal gets generated, right? So this hexagon over here, it is the basic structural unit, which upon repeating, generates the entire crystal, right? So the unit cell that gets generated over here, that is hexagonal. Unit cell is called as hexagonal unit cell in 2D. It's called as hexagonal unit cell in 2D. Since the unit cell generated is hexagonal in shape, that's why we call this packing as hexagonal close packing in 2D as well. This is called as hexagonal close packing in 2D as well. Correct? Now, dear students, one more thing. Can you let me know how many particles are touching this particular particle simultaneously? 1, 2, 3, 4, 5, 6. 6 particles are touching one particular particle simultaneously. That means the coordination number of each particle in this hexagonal close packing in 2D, that's 6. Okay, right? Now, dear students, if you ask me, what about the rank of the unit cell? What about Z value? Rank of this unit cell over here. In this particular hexagonal unit cell, there are two types of particles. Corner particles and the one at the center. Corner particles and the one at the center. What about the contribution of this particular corner particle? Is it completely inside? No. This particular corner particle, it is shared by 3 hexagons. This is one hexagon, one on this side, and one here on the top, right? So this particular particle is shared by 3 hexagons. So its contribution towards the unit cell is 1 by 3. And how many such kind of corner particles we have here? Apart from that, one at the center, which is completely inside it. So its contribution is 1. So the value comes out to be 2, 1, 3, 1, 3, 2, 2 plus 1 comes out to be 3, right? So rank of this particular hexagonal unit cell in 2D, it's 3. Rank of this particular unit cell, hexagonal unit cell in 2D, it is 3, correct? Now only one parameter is left. That's packing efficiency. Since we are doing packing in 2D, so I won't be talking in terms of volume. I'll be talking in terms of area, right? So I'll say area of the particles, area of constituent particles inside the hexagon divided by area of unit cell, matlab area of hexagon multiplied by 100, right? Now let's try to calculate it. Area of constituent particles inside this hexagon. Area of constituent particles inside this particular hexagon. Inside this hexagon. Understand? If you talk about this whole particle, its area is pi r square. Can you let me know what part of area of this particle is inside the hexagon? I mean this particular part, shaded part. Pi r square is the area of whole particle. I'm multiplying it with 1 by 3. So 1 by 3 into pi r square. It is that area of this corner particle which lies inside the hexagon. How many such kind of corner particles do we have? 6. So what did I calculate till now? I got that area of all the corner particles. That area of all the corner particles which lies inside this hexagon. Apart from that, there is one particle exactly at the center, right? Which is completely inside the hexagon. So I have to take its whole area, which is pi r square, divided by area of hexagon. How do we calculate the area of hexagon? That is the point now. How do we calculate the area of hexagon? My dear students, can I say a hexagon, it is basically made up of 6 equilateral triangles. Hexagon is made up of 6 equilateral triangles. Area of one equilateral triangle is root 3a square by 4. It is the area of one equilateral triangle. I'll be just multiplying it with 6. This whole term I'll be calling as area of hexagon. Simple. Multiplied by what? Multiplied by 100. Okay. Now the point is what this A is all about. Write this A in terms of R. What is A? A is the edge length, the distance from here to here. This is A. The distance from here till here. It's A. can I say A is equal to R plus R, which makes it 2R. So instead of A, you can write 2R here. Instead of A, you can write 2R here. So let me write it completely. It's going to be root 3 A square, 2R square. Divided by what? Divided by 4. Correct? Now, dear students, a bit of calculation is left. R square, R square, R square, everywhere cancelled, right? Put the value of pi and all. You'll be getting the final packing efficiency approximately equal to 91%. Now, you guys are going to let me know what this 91% means. What this 91% means. Does it mean out of the total volume of the unit cell? No. It means out of the total area of the unit cell, 91% area is covered by the particles. Out of the total area of the hexagon, out of the total area of the 2D hexagon, 91% area is covered by the particles. What about the remaining space? Remaining space will be empty. And empty space is something which you call as voids. So percentage of voids approximately will be 9%. I hope it's clear. I hope it's super clear to you. Right? Is it clear to everyone? So now, in case of 2D, how many packings do we have? In case of 2D, we have two types of packings. Let me summarize all this. When we talk about the two-dimensional packing, in case of two-dimensional packing, we have got two types of packings. One is called as AAA packing in 2D. One is called as ABAB packing in 2D. ABAB packing in 2D, right? In case of AAA packing in 2D, which unit cell is generated? Square unit cell is generated, right? In case of ABAB packing in 2D, hexagonal unit cell is generated, but it is the hexagonal unit cell in 2D, right? Now, the value of Z over here came out to be, it was 1, I guess. Yeah? 1 by 4 into 4, 1, yeah. The value of Z over here, it was 3. Okay? Perfect. Now, if I ask you the coordination number, over here it was 4, and right here it was 6. If I ask you about the packing efficiency here was 78.54%, and the wide percentage was 21.46%. When it comes to your hexagonal unit cell, its packing efficiency was approximately 91%, and the wide percentage was approximately 9%. Now, if I ask you, in 2D, which one is more efficient packing? In 2D, which one is more efficient packing? You tell me the answer in the chats quickly. In 2D, which one is the efficient packing? Is it AAA or ABAB? Which one is more efficient? Which one is more efficient? Quickly. In 2D, I'm asking. In 2D, which one is more efficient? Is it AAA or ABAB? It's absolutely going to be ABAB packing in 2D, which is more efficient over here when it comes to packing. Right? Clear to everyone? If this is clear, let me give you one question. Let me see if you can solve this or not. Let me give you one question. For example, I'm giving you a two-dimensional arrangement. I'm giving you a two-dimensional arrangement of constituent particles. Let's say the arrangement is like this. This is one particle here. This is one more particle. One more particle. One more particle. And one same size particle at the center. I could not make it properly, but it is the similar particle of the same size, right? Now, dear students, I'm joining the centers of these particles. I'm joining the centers of these particles. After joining the centers, the unit cell which we got over here, that's square in shape. For example, the unit cell that is being generated here, this is the unit cell I'm talking about. This is the two-dimensional arrangement wherein the unit cell which got generated, that is square in shape. I'm assuming that the length of this square is A. The length of this unit cell is A. And I'm assuming that the radius of each particle is R. Radius of each particle is R. I'm asking you to calculate the packing efficiency. Can you do it? I'm asking you to calculate the packing efficiency. What do you think? Can you solve it? Can you solve it? The unit cell is square in shape. I want you guys to calculate the packing efficiency. How do you do it? Which formula will you use? Will you talk in terms of area or in terms of volume? It is two-dimensional arrangement, so I'll be talking in terms of area. I'll write packing efficiency is equal area of constituent particles inside the unit cell divided by area of unit cell multiplied by 100. This is how we do it. Now guys, understand. You might make mistake at one point. And what is that? You'll get to know in some time. Have a look. Area of constituent particles inside. Since this is the unit cell, how many different types of particles this unit cell contains? It has got 4 corner particles and 1 exactly at the center. So there are 2 types of particles, corner and the center one. Now if I ask you, is this whole corner particle inside the square? No, only 1/4 part of it is inside. Similarly, 1/4 part of this one is inside. 1/4 part of this one is inside. 1/4 part of this one is inside. So what area of this corner particle is inside the square? Let's assume area of the whole corner particle is pi r square. Area of the whole corner particle is pi r square, right? This is the area of one whole corner particle. But entire corner particle is not inside the square, only 1/4. So multiplying it with 1/4. So this is the area of one corner particle which is inside the square. And how many such corner particles do we have? We have got 4 corner particles like this. Apart from that, there is one particle which is exactly at the center, which is wholly and solely inside the square. So I'll have to take its entire area, right? So I got to know the area of all the constituent particles that lie inside the square divided by area of unit cell, area of square, which has to be side square, a square, multiplied by 100. Now, my dear students, if you're thinking you'll replace a with 2r, that means you are doing something wrong. That means your question will be wrong. A won't be equal to 2r. Is this A? A is the distance from here to here. Is it equal to 2r? See, from here to here it's r. From here to here it's r, right? Then from here to here it's r. What about this distance which is in between? So A is actually greater than 2r. A is not equal to 2r. A is greater than 2r. Now the point is, how can you write A in terms of r? That is the point here. How can you write A in terms of r? There is one more way. See, if you join this particular particle and this particular particle, if you join these two, let me call this as A, let me call this as B, let me call this as C. In triangle ABC, AB length is A, BC length is A. What about AC length? AC length has to be root of 2A. Now this AC length, which is, I can call this as phase diagonal. Okay, I can call this as diagonal. Perfect. Now you can see this particular particle, it is touching the one at the center. The one at the center is touching this particular one. So these 3 particles are basically touching each other. So can I say AC, which is equal to root of 2A? It will be equal to R plus R plus R plus R. So R plus R plus R plus R makes it 4R, right? So root of 2A is basically equal to 4R. So from here you can calculate A, which will be 4R divided by root 2, or you can write it as A divided by 2 root 2. Perfect. So it's equal to R by 2 root 2, sorry. Just a second, I made a mistake. So you can write A is equal to 4R divided by root 2 over here. So instead of A over here, it was A square, right? Instead of A square, you can write 4R divided by root 2 ka square. Now it's just a matter of calculation. R square gets cancelled out. Put the value of pi, right? Put the value of pi and get the exact value as 78.54%. So what is the 78.54%? It is the packing efficiency. It is the packing efficiency which we were supposed to calculate of this particular two-dimensional unit cell. What does that mean? That means out of the total area of the unit cell, 78.54% area will be covered by the particles. The remaining area will be empty. I hope this is clear. So this was your two-dimensional packing. Now, my dear students, let's enter into three-dimensional packing. I hope it's clear. Yeah. Let's enter into three-dimensional packing. So I'm marking the heading as close packing in 3D. Now I'm going to arrange the constituent particles along x-axis as well as y-axis as well as z-axis. I'm going to arrange the constituent particles along all the axes, right? The point over here is, in close packing in 3D, we have to discuss three types of packings. One is AAA packing in 3D, which we shall be discussing. One is AB packing in 3D, which we shall be discussing. One more is ABC packing in 3D. These will be the three different packings which we shall be discussing in close packing in 3D. Okay? Now let's try to understand one by one what it means. For example, you have got AAA packing in 3D. Perfect. My dear students, over here, understand what exactly I'm going to talk about. Till now, I was placing rows, right? Now I'll be placing layers. I'll be talking in terms of layers. Layer 1. Above layer 1, there is layer 2. Above layer 2, there is layer 3. Now I'll be talking in terms of layers. I won't be talking in terms of rows. Okay? Yeah? Have a look. For example, understand. Understand, guys. First of all, this particular sheet of particles, this layer of particles, I'm calling as layer A. This particular layer of particles, this particular sheet of particles, I'm calling as layer A. This is the first layer. This is the first layer, okay? This is the first layer. Perfect. Now, my dear students, one simple thing. Right now, it's close packing in 2D. It's similar like close packing in 2D. Perfect. It's your layer 1, which I call as layer A. Yeah. So first of all, in the layer A, if you join these, what do I get? In the layer A, you are getting a square. In the first layer, you are getting square, right? You are getting square. Let's say this is the square which I'm drawing over here, right? And in this square, you have got 4 corner particles. I'm mentioning these 4 corner particles like this. Perfect. And basically, these particles are touching each other. This particle is touching. That means this one and this one, they'll be actually touching. This one and this one, they'll be touching. This one, they'll be touching. This one, they'll be touching. So in the layer A, what do I get? In the layer A, I'm getting square. If I'm joining the centers, I'm getting square. This is the first layer. Now, what about this was the first layer of particles. What about second layer? Second layer is again layer A. What does that mean? What does that mean? That means you are going to place one more layer of particles exactly on the top of the first layer particles. On the top of this particular particle, then on the top of this particle, on the top of this, on the top of this, on the top of every particle. Perfect. So if square got generated in the first layer, that means in the second layer, can I say one more square will get generated? In the second layer, one more square will get generated. Because first layer and second layer, they are same. First layer, second layer, they are same, right? In the first layer, a square got generated. Similar square will get generated in the second layer when you will place the second layer particles on the top of first layer. I hope you're getting it. Similar square got generated over here, right? I'll say these two will be touching, these two will be touching, right? Perfect. And my dear students, one more thing. See, this is the particle of layer 1. On the top of it, there is particle of layer 2. Yeah? On the top of it, there is particle of layer 2. Perfect. This is particle of layer 1. On the top of it, there will be particle of layer 2. So if I have a look on this particular particle means I'm talking about this one. I'm talking about this one. I'm talking about this one. Perfect. On the top of it, there will be one more particle. And that one more particle is this one. So if there is one particle on the top of this one, that means these two particles will be also touching each other. These two particles will be also touching each other. I could not make it properly, but I hope it's fine. How does it look like? How does it look like? Does it look like a simple cubic unit cell in which the particles are present at only corners? So my dear students, when I talk about the close packing in 3D, which involves AAA packing in 3D, in AAA packing in 3D, the unit cell that gets generated, that is SCC, which we have already discussed, correct? So this is the only point which you have to remember here. This is the only point which you have to remember here. So in case of your AAA packing in 3D, in case of your AAA packing in 3D, the unit cell that gets generated, that is SCC. And we have discussed SCC in detail, right? Do you remember? For SCC, Z value is equal to 1. For SCC, A is equal to 2R. For SCC, packing efficiency is equal to 52.4%. For SCC, void percentage of void is equal to 47.6%. For SCC, the coordination number of each particle is 6. So basically, all these parameters which we have already discussed, they are actually the parameters of AAA packing in 3D. For example, if they ask you a question, what about the packing efficiency in case of AAA packing in 3D? What about the packing efficiency in case of AAA packing in 3D? You have to remember only one thing. In case of AAA packing in 3D, the unit cell generated is SCC. And for SCC, we have discussed packing efficiency is 52.4. So 52.4% is the packing efficiency. Coordination number is 6. Right? If they ask you what is the coordination number for each particle in AA packing in 3D, coordination number is going to be 6. Right? Is this clear to everyone? Let me know quickly. Say yes or no in the chats. Quickly, guys. Is this super clear? This was layer A. Now on the top of it, you are going to place one more layer. Imagine this is one layer. This, my hand, is one layer. On the top of it, you are placing one more layer. Right? Then on the top of it, one more layer. Right? So if the square got generated in the first layer, that means in the second layer, one more square will get generated. In the third layer, one more square will get generated. Right? I hope all these things are clear. Perfect. So this was your AAA packing in 3D. Now, the second packing, that's called as ABAB packing in 3D. This is something which you have to understand. You have to imagine things. ABAB packing in 3D. See how it looks like. Understand how it's looking. My dear students, the first layer of particles, see how it looks like. This is the first layer of particles. Can I say the first layer of particles looks the same? The first layer of particles, it looks the same as was ABAB in 2D. Yeah. Well, look on this properly. The first layer, which I'm calling as layer A, does it resemble with ABAB packing in 2D? Yes, it resembles with ABAB packing in 2D. The first layer, right? Now it's 3D. It's 3D. You have to put one more layer on the top. You have to put one more layer on the top. But before putting one more layer on the top, just have a look. Join these points. Join these centers. What do I get? In the first layer, I'm getting a hexagon. In the first layer, I'm getting a hexagon. So, let me show you the first layer over here. In the first layer, we are getting one hexagon. Perfect. And in this hexagon, the particles are present at the corners and one at the center. So, these are the corner particles, which I'm showing like this, and one at the center. Perfect. So, the hexagon got generated in the first layer. It is a 2D hexagon which got generated. Perfect. So, this was your layer A. Now, second layer, layer B. Will first and second layer resemble? Will they be same? Will they be same? No, they cannot be same. They cannot be same, right? So what does that mean? Should the second layer particles be exactly on the top of first layer particles? No. Then second layer name should have been layer A, but it's layer B. So second layer should not be identical to first layer. So second layer particles should not be at the top of first layer. They should be kept in the depression. second layer particles should be kept in the depressions. These are the depressions. These are the depressions, right? So let's fill the depressions over here. Let's fill the depressions over here. How many voids do you see over here? 1, 2, 3, 4, 5, 6. 6 voids you are seeing. But all these 6 voids cannot be filled. Alternate voids will be filled. Whatever voids you are seeing in this layer, whatever depressions got created, all these depressions cannot be filled. Only alternate depressions can be filled. So in this hexagon, if I'm filling this particular one, and this particular one, so 3 will be filled. So in the second layer, what is the shape which you are getting? In the second layer, you are getting a triangular shape. In the second layer, you are getting a triangular shape. Imagine this is the second layer. This was layer A, in which hexagon got formed. In layer B, a triangle got formed. Look at the third layer, my dear students. Third layer is again the layer A. Third layer is again the layer A, right? If third layer is again the layer A, that means third layer resembles with the first layer. In the first layer, hexagon got created. That means in the third layer also, hexagon will be getting created. In the third layer also, hexagon will be getting created. In which particles will be at the corners and one at the center. If this is A, this is B, this has to be A as well. Perfect. Now, my dear students, if you exactly join it, what kind of structure did you get? Say, imagine this is one benzene ring, 2-dimensional. This is 2-dimensional. Joining 2 benzene rings, you got one 3-dimensional hexagon over here. You got one 3-dimensional hexagon over here, right? So the unit cell which gets generated in this particular packing, it is a 3-dimensional hexagon. It's a 3-dimensional hexagon, right? It's a 3-dimensional hexagon. It is the unit cell which got generated over here. Perfect. This is the unit cell which got generated over here. 3-dimensional hexagon. In the first layer, a 2D hexagon got generated. In the second layer, a triangular shape. In the third layer, again, 2-dimensional hexagon. So entire diagram I'll be calling as 3-dimensional hexagon. Okay, so unit cell over here which got generated, that's called as 3D hexagon. Now guys, if I ask you a few important things. This is the hexagon which got generated. This is the unit cell. What about the Z value? What about the Z value for this unit cell? Can you calculate Z value for this unit cell? Exactly, it's like a box, right? It's like a box. Can you calculate Z value for this hexagon? First of all, understand how many types of particles do we have here? How many types of particles do you see? See, in this 3-dimensional hexagon, you can see this is corner particle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 corner particles, right? Face center, 2 face-centered particles, and 3 particles inside this hexagon, Perfect. These are the 3 different types of particles. Corner particles, face-centered ones, and 3 particles inside the hexagon, correct? Right? Now people, if I ask you, what is the contribution of this particular corner particle? What is the contribution of this particular corner particle? What do you think? What is the contribution of this particular corner particle? Don't say 1 by 8. It's not going to be 1 by 8. It's not going to be 1 by 8. Clearly have a look. Or if it makes a bit, if it is really difficult to imagine, tell me the contribution of this particular corner particle. What do you think? Have a look. Let's say exactly with how many this kind of hexagons, with how many 3-dimensional hexagons this particle is being shared with. This is one hexagon, right? And I say on side of it, there'll be one more hexagon whose top surface is this one. This is that hexagon which I'm talking about, right? Can I say behind it, there'll be one more hexagon whose top surface is this one? Perfect. Whose top surface is this one? So in the ground floor, this is the ground floor. In the ground floor, with how many hexagons this particle is being shared with? It's shared with 3 boxes. It is shared with 3 hexagons. This is 1, there's the second one, and behind it, there's a third one, right? Can I say, similarly, 3 more hexagons will be present at the top of them. 1 hexagon at the top of this, 1 hexagon at the top of this, 1 hexagon at the top of this, right? Or I can say these 3 surfaces, this particular surface, and this particular surface. No doubt, these are the top surfaces of these hexagons. At the same time, the same 3 surfaces, these are the bottom surfaces of the hexagons which are present in the first floor, right? The same 3 surfaces, These are the bottom surfaces of the further 3 hexagons which are present in the first floor. So now tell me, with how many total 3-dimensional hexagons this corner particle is being shared with? Is it shared with 6 hexagons in total? Is it shared with 6 boxes? This is box number 1. This is 2. Behind it, 1 more, 3. And 3 at the top. So the contribution of this corner particle is 1/6. And how many such corner particles we have? In one hexagon, 12 corner particles. Right? Apart from that, contribution of this face-centered particle, 1 hexagon downwards, 1 box downwards, 1 box upwards. So 1/2. Contribution of 1 face-centered. And how many such face-centered we have? 2 face-centered. Apart from that, 3 particles exactly at the center. Contribution of 1 is 1, and there are 3 in total. So what is the value which we get over here? The value over here comes out to be 6. So I'll say 6 particles per unit cell. 6 particles per unit cell, right? If you ask me, what about the coordination number of each particle here? What about the coordination number of each particle? Let me select the simplest particle, this one. Tell me how many particles will be touching this particular particle simultaneously? In the first layer, the middle particle, that is this one. In the first layer, the middle particle, that is this one. Okay? This middle particle is being touched by the 6 particles in its plane. So these 6 particles are first of all touching it, number 1. Number 2, this middle particle, at the top of it, there are 3 more particles. So these 3 are also touching it, right? So this is A, this is B, this is A. Just below A, what will come? B will come. So B will be like this. There will be 1 more triangle here. And these 3 particles will be also touching it. So towards this particular particle, how many particles are touching? 12 particles. So coordination number of particles in case of your AB packing, that is 12. Okay? This was A, this was B, this was A. Just below A, there will be B, right? Yeah? Perfect? Madhavan, just drag the video a little back. This is a bit confusing. Okay, drag the video a little back, it will be clear. Perfect? And do remember, this is something which I'm not going to derive, so I want you guys to remove the result directly. Packing efficiency of this hexagonal unit cell, it is 74%. Okay, that means the percentage of voids in hexagonal unit cell, it is equal to 26%. Perfect. All these parameters I want you guys to remember from now on, related to this particular packing, AB packing. Perfect. Now guys, there is one more packing. Let's not get into the details of it. Let me just give you the conclusions from which the questions can come. ABC packing in 3D. Only one thing you need to remember. The unit cell that gets generated here, that is FCC. And whatever parameters we have discussed about FCC, all those are actually the parameters of this packing. The Z value for FCC, that is 4. R is equal to A divided by 2√2. Then we have got packing efficiency, 74%. Void percentage, 26%. Coordination number of each particle, that's 12. Right? Just remember this thing. That's more than sufficient. Okay? In case of ABC packing in 3D, the unit cell that gets generated is FCC. If they ask you, what is the coordination number of each particle in ABC packing in 3D? You'll say in ABC, FCC gets generated. In FCC, coordination number is 12. So the coordination number of each particle in ABC packing is 12 only, right? Perfect. Let me tell you This FCC, sometimes you can call it as CCP as well, cubic close packing. In the questions, they might divert you sometimes. Instead of the term FCC, they will mention CCP, and CCP stands for cubic close packing. CCP stands for cubic close packing. Do remember, this cubic close packing is nothing but FCC. In the question, they might divert you at times. I hope all these things are clear, right? I hope all these things are clear. So you got to the idea about the A packing in 3D, AB packing in 3D, ABC packing in 3D. Yeah? Perfect. Now guys, one more important thing. I did not discuss about the voids yet. What are voids? Voids are the vacant spaces in between. Right? Voids are the vacant space in between. How many different types of voids do we have? Let's have a look. Let me just give you the idea of voids first. The first type of void is something which you call as trigonal void. Right? Then you have got tetrahedral void. Then you have got octahedral void. And then you have got cubic void. These are the different types of voids which get created basically. But out of these different types of voids, we have to discuss two types of voids only. One is tetrahedral void and one is octahedral void. These two voids we have to discuss in detail, right? Let me give you the idea about all these voids. Trigonal void is formed when three particles, trigonal void is formed when three particles touch each other. Three particles are touching each other. The void which got generated in the middle, right, which is trigonal in shape. This is something which I call as trigonal void. Since this trigonal void is formed when three particles touched, so do remember coordination number of this particular void is 3. Coordination number of this particular void is 3. And by chance, if any small particle enters into this void, coordination number of that smaller particle will be also 3. If by chance any small particle fits this void, properly fits this void, the coordination number of that small particle will also be. Point number 1, simple and basic, right? Now, dear students, tetrahedral void. It gets generated when 4 particles touch each other. 3 over here and 1 at the top. For example, 1 at the top. The void which got generated in the middle, it got formed when 4 particles touched each other. And any such void which gets generated when 4 particles touch each other, that's something which you call as tetrahedral void, whose coordination number is 4. And if by chance any small particle fits this tetrahedral void, its coordination number also will be 4. Okay? Talking about the octahedral void, how this octahedral void looks like. Octahedral void simply looks like this. Have a look. Okay? 3 over here and 3 more particles above it. 1 particle, 1 more, and 1 more over here. The void which gets generated over here in the middle, which got generated by when 6 particles touched each other. This particular void is something which we call as octahedral void, which is getting formed when 6 particles are touching. So its coordination number has to be 6. And if by chance any small particle fits into this void over here, its coordination number will also be 6. Okay. Now talking about the cubic void. Four particles over here and exactly 4 particles on the top of them. And exactly 4 particles on the top of them. 1 more particle on the top of first particle, on the top of it, on the top of it, on the top of it. And all the particles in the second layer, they are also touching each other. That means 2 yellow particles will be also touching. These 2 yellow particles will be also touching. These 2 yellow, these 2 yellow. So in between the void which got generated, when 8 particles in total are touching each other, you are calling this as cubic void, which got created when 8 particles are touching. So its coordination number has to be 8. So this is just the general overview of different types of voids. General overview. This was a general overview of different types of voids. But two voids we have to discuss in detail. One is tetrahedral, one is octahedral. One is tetrahedral and one is octahedral. So let's try to understand them in detail. This was a quick overview of different types of voids and their coordination number. Okay. So now the actual topic is your tetrahedral and octahedral voids. Okay. First of all, first thing which I'm going to write over here. Do remember the number of octahedral voids in a unit cell. Number of octahedral voids in a unit cell is always equal to the value of Z. Whatever is the Z value, same is the number of octahedral voids in a unit cell. Similarly, if they ask you the number of tetrahedral voids in a unit cell, it is always equal to the value of 2 times Z. What does that mean? That means the number of tetrahedral voids in a unit cell is always equal to 2 times the number of octahedral. 2 times the number of octahedral. That's what it means exactly. For example, you have got simple cubic unit cell, right? You have got simple cubic unit cell. What is the value of Z for simple cubic unit cell? That's 1. That's 1. Value of Z for simple cubic unit cell is 1. Okay. If the value of Z is 1, so tell me how many octahedral voids will be there? 1. How many tetrahedral voids will be there? There will be 2. Okay. In simple cubic unit cell. In simple cubic unit cell, there will be some, like in the unit cell, you saw there are voids present. What percentage of voids? What percentage of void is present in SCC? 47.6%, right? Now, what type of void that is? Is that triangular void? Is that tetrahedral? Is that octahedral? That's something we have to discuss. So in SCC, I'm just telling you one result. In SCC, the value of Z is 1. If the value of Z is 1, that means in SCC, there will be 1 octahedral, 2 tetrahedral voids. If you talk about BCC, for BCC, the value of Z is 2. So how many octahedral voids? 2. How many tetrahedral voids? 4. Based on the result which I gave you over here, right? Perfect. Now guys, talking about FCC, the value of Z is 4. Okay, the value of Z is 4. That means there will be 4 octahedral voids and there will be 8 tetrahedral voids in total in FCC. Yeah. Similarly, we discussed about hexagonal unit cell in 3D as well. In hexagonal unit cell in 3D, the Z value was 6. Z value was 6. That means octahedral voids will be 6, tetrahedral voids will be 12. So first thing, you should know exactly how many different types of voids are present in different types of unit cell. You should know that. Density of unit cell also we'll discuss after this. Just concentrate on what I'm saying, okay? Just, I know density is pending. There's a formula for that. That's something like complicated topic. That's simple formula based. After some time, I'll teach that. Just understand this. So this is one type of question which can be asked. How many octahedral voids are present in different types of units? How many tetrahedral voids are present in different types of units? Okay. My dear students, what we have to discuss in detail. This is something which is in our syllabus basically. This is something which is in our syllabus. The location of tetrahedral and octahedral voids in FCC. We have to exactly see how in FCC tetrahedral and octahedral voids are generated. Okay. So I'm marking the heading over here as location of. This is something very important. Location of octahedral voids and tetrahedral voids. In what? In FCC. This is something very, very, very important. And this might be confusing too for some people. So I would want you guys to have a look at it properly. Okay. First of all, in case of FCC, when you talk about octahedral voids are present at edge centers. Octahedral voids are present at edge centers and at body center. How exactly they are generated, you will see in some time. Number 2, tetrahedral voids are present at 1/8 of body. Sorry. Tetrahedral voids are present at 1/4 of body diameter. 1/4 of body diameter. Let's try to decode these statements. Understand. So first of all, I'll make you understand. How octahedral voids in FCC are present at edge centers and at body center. Now guys, Please and please have a proper eye on this particular structure. I'm going to make one FCC. I am going to make one FCC. Okay, I'm going to make one FCC in which particles are present at corners. Apart from corners, they are present at the center of each face. Center of front face, center of back face. Okay, this one FCC. Now guys, one statement I'm going to give you. How can we? I mean, what all things we need to remember over here? Understand? First thing, this is FCC, right? In case of FCC, we have discussed that. In case of FCC, we have discussed that face diagonal particles. Face diagonal particles, they touch each other. And do remember, adjacent face centered particles. Adjacent face centered particles, they also touch each other. Adjacent face centered particles also touch. Now, what does that mean? I'll first of all show you how octahedral void is generated, is formed at the body center. Okay, is formed at the body center. But dear students, if you look at this particular face, this is the face centered particle of it, right? Side face. If you talk about front face, this is its face centered particle. Should I be calling these two particles as adjacent face centered particles? One here, one on this one. I hope you're getting it, what I'm trying to say. This particular face over here, imagine it's like this. The front face is, for example, like this. The front face is, for example, like this. So this is how they are. One particle is present at the center of one face and one more at the center of one more face. So should I be calling these face-centered particles over here as, what do I call these face-centered particles? Adjacent face-centered particles, right? So these two are adjacent face-centered particles. Similarly, my dear students, this particular particle and this particular particle, these two are also the adjacent face-centered particles. Similarly, this one and this one, they are also the adjacent face-centered particles. Similarly, this one and this one, they're also the adjacent face-centered particles. I hope you are visualizing which particles these exactly are. This is the face center of front face. This is the face center of back face. This is the face center of side face. Face center of side face. Yeah. So this one and this one, adjacent face center. This one and this one, adjacent face center. This one, adjacent, right? So I can say these two are adjacent face centers. If these two are adjacent face centers, that means these two particles will be touching each other. Now imagine how they'll be touching each other. Imagine how they'll be touching each other. This particle and this particle, they should be touching each other. This one and this one, they should be touching each other. This one and this one, they should be. Even these two should be. So, can you let me know, in this plane, which I showed you over here, how many particles are basically touching? It is basically 4 particles touching in this plane. In this plane. This one and this one are touching. This one is touching this one. This one is touching this one. So 4 particles are touching basically in this plane. My dear students, if these 4 particles are touching, can I say a vacant space would have got generated in the middle? This one touching, these two are touching, these two are touching, these two are touching. Can I say vacant space would have got generated in the middle? Right? Above that vacant space, you have got this particle. Below that vacant space, you have got this particle. A vacant space got generated in the middle, exactly here, right? Exactly at the center of the cube. But at the top of that vacant space, there is one particle. Below that vacant space, there is one more particle. So, my dear students, can I say a void got generated at the center of the cube, basically? A void got generated at the center of the cube. And this void got generated when how many particles are touching? When 6 particles are touching each other. And which kind of void gets generated when 6 particles touch? Octahedral void. So should I be calling this particular void, which got generated at the center, as the octahedral void? Absolutely. This is something which you call as octahedral. So octahedral void is present at the body center. It gets formed at the body center. So till now, whatever questions I used to give you, I used to tell you sometimes that a particle is present at the center of the cube. If it was FCC, at the center of cube, there is basically the octahedral void. That means that particle has entered the octahedral. Yeah. This is the void over here, which is octahedron in shape. It is octahedral. Haven't you seen SF6 structure? Haven't you seen octahedral structure? Right? In chemical bonding, you would have studied somewhere, right? This is what we call as octahedral. Don't you think you got one octahedron kind of structure over here? So this particular void which got generated at the center, I'll be calling this void as octahedral. Perfect. Now, octahedral voids are formed at edge centers too in case of FCC. Now, how exactly at the edge center? How exactly at the edge center? Understand. If I consider this particular edge, I need to show you at the center of the edge, octahedral void gets generated. But how exactly? We know in case of FCC, phase diagonal particles also touch. So this is the phase diagonal. So this particle and this particle, they should be touching each other. Even this is the phase diagonal. This is the phase diagonal. So this particle as well as this particle, they'll be also touching each other. On the side of it, there'll be one more phase, right? If this is FCC, this also has to be FCC. At the center of it, there should be a particle. This is a phase diagonal, right? If this is one more phase diagonal, that means these two particles should be also touching. One more phase diagonal, these two particles should be also touching. So these four particles here are touching in one plane. They are touching in one plane. One, these two, these two, these two, and these two. They are touching in one plane. Perfect. And when these four particles will be touching, can I say a vacant space would have got generated in the middle? Right? Now below that vacant space, you have got this particle. You have got this particle. Below that vacant space, you have got this particular particle. And above that vacant space, you have got this particular particle. Just have a look. Can I say at the center of the edge, do you see a void getting generated which is formed when these six particles are touching, four in one plane, one above it, one below it? It looks like one more octahedron. So this empty space over here, is something which you will be calling as octahedron. Hope it's clear. So octahedral void, as I told you, it's formed at edge center and body center. This is the edge centered octahedral void. This is the body centered octahedral. Right? Is it clear? One is edge centered octahedral void, one is body centered octahedral void in FCC. All clear? Yeah? Now one more thing. I told you octahedral voids, they're present at edge centers and at body center. Can you tell me? This edge-centered octahedral void, it will be shared between four cubes. The way I used to tell you, edge-centered particle, its contribution used to be 1/4. Even this octahedral void at the center, at the edge center, even it will be shared between four cubes. This is one cube. This is your one more cube. This is your one more cube, and this is your one more cube. Right? It's shared between four cubes. It's a common edge to four cubes. That means the octahedral void which is getting generated here, it will be also common to four cubes. So its contribution is 1/4. Edge-centered octahedral void, 1/4 contribution. How many edge-centered octahedral voids will be there? There are total 12, let's say. Right? Apart from that, one at the body center. At the body center, the contribution is 1. And there is 1. The value comes out to be 4. So in total in FCC, how many octahedral voids will be there? There will be 4 octahedral voids, which I discussed already. In case of FCC, how many octahedral voids will be there? In total 4. Out of which these are the edge centered and this one is the body centered. So total there will be 4 octahedral voids in FCC. Clear? Now if you talk about the tetrahedral voids are present at 1/4 of the body diagonal, right? They're present at 1/4 of the body diagonal. Perfect. So let me just show it to you. Imagine that we have got one FCC. Imagine that we have got one FCC. Perfect. We have got one FCC. Now I'll show you exactly where the void gets generated. Particles are present at the corners. Apart from the corners, they are present at the center of each face. Front face, back face center. Okay. Now, my dear students, one simple thing, understand one thing. If I consider this particle, can I say this one and this one, they'll be touching each other? Because they are phase diagonal particles. Even this one and this one, they'll be touching each other. They are phase diagonal. This one with this one, because they are phase diagonal, right? This one with this one, they'll be touching each other. Imagine that, how, see, first of all, this is the center of the back face. This is the center of back face. This is the center of top face. This is the side of, this is the center of side face. This one and this one, they are touching. This one and this one, they are touching. This one and the back face center, they are touching. Right? Can I say it looks like a tetrahedron kind of a thing? Tetrahedron kind of a thing, it's going to be. Right? Imagine that this is one particle. Right? Imagine that on one side there is one more. On one side there is one more. And just behind the board there is one more. This one is touching this. This one is touching this. This one is touching this. Can I say a vacant space got generated here? And that vacant space is getting generated when 4 particles are touching. When 4 particles are touching. I hope you're exactly getting what I'm trying to say. Right? This is one particle. This is the corner particle. This is the one particle which is touching it. Right? This one. One more particle which is touching it. This one. Right? This particular particle, it is behind the board. It is behind the board basically. And they are also touching. Right? So these 3 particles, they are touching this particular one. Perfect. Imagine that they are touching. So can I say in between, vacant space got generated? That vacant space is basically your tetrahedral wide. I hope you can imagine this. I hope you're imagining this. This one, this one, this one. I mean, these 3 are touching this one simultaneously. So a vacant space got generated, and which is exactly located at 1/4 of the body diagonal. Which is exactly located at 1/4 of the body diagonal. Let me show you where exactly. Let me show you where exactly. I'm again going to make one FCC. I'm again going to make one FCC. Okay? One of the body diagonals I'm going to show you. For example, from here till here. It's one of the body diagonals. Perfect? I'm dividing this body diagonal into 4 parts. Right? This part, which I call as 1/4, even this part, which I call as 1/4 of the body diagonal. Here you will find this tetrahedral wide, which is getting generated. It is at 1/4 of body diagonal. Even this is 1/4 of the body diagonal. At 1/4 of each body diagonal, what do we get? We get a tetrahedral wide. We get a tetrahedral wide. At 1/4 of each body diagonal, you'll be getting a tetrahedral wide in FCC. Now, in case of the cube, how many body diagonals can we draw? We can draw 4 body diagonals. On one body diagonal, there are 2 tetrahedral wides. That means total on 4 body diagonals. How many tetrahedral will be there? 8 tetrahedral wides will be there in total. Right? On one body diagonal, you'll find 2 tetrahedral wides. But there are 4 body diagonals. So on 4 body diagonals, you'll find 8 tetrahedral. That's what I wrote in the beginning. There are total 8 tetrahedral wides in case of FC. I hope all these things are. You must be thinking, where do we use all these concepts? Where do we use all these concepts? Before talking about the concepts, let me show you one important thing. So do remember this particular thing. When you talk about octahedral and tetrahedral wides in FCC, octahedral wides are present at edge centers. Remember it finally. Octahedral wides, they are present at edge centers and body center. Tetrahedral wide is present at 1/4 of body diagonal. Just remember this thing only. This much is enough. Right? Now, there is one more simple topic which I need to tell you. That can be a question asked. Location of, or let me not talk about the location. Let me talk about the distance between two nearest octahedral wides in FCC. This can be the question asked. What is the distance between two nearest octahedral wides in FCC? Now you all know, you guys already know, in case of FCC, octahedral wides are present at the edge centers and the body center, right? You already know that. For example, this is the FCC. Let's say this is one FCC. in FCC, where do you see the octahedral voids? You see the octahedral voids at edge centers and body center. So can I say this is one edge, at its center you will find one octahedral void? Absolutely. Right? Yeah. Can I say on this edge center you will find one more octahedral void? I showed you exactly how octahedral void is generated at the center of the edge. Right? Now I'm directly telling you, at this center you'll find octahedral void. At this center you'll find octahedral. These two are the nearest octahedral voids. Right? These are the nearest octahedral voids, you can say. So, what is the distance between them? Let me call this as point A, point B, point C. I need to get the distance between A and C. I need to get the distance between AC. AC distance we have to calculate. Isn't it very simple? Now have a look. AB, let's say the edge length of the cube is A. If the edge length of the cube is A, so AB is going to be A by 2, BC is going to be A by 2. So AC is going to be under root of. AC is going to be under root of A by 2 square plus A by 2 square. Right? A by 2 square plus A divided by 2 square. So AC length is going to be equal to under root of A square by 4 plus A square by 4. 2 times A square by 4, which is A square by 2. So AC is going to be equal to A divided by under root 2. This is the distance between two nearest octahedral voids in case of FCC. This can be a question directly asked. This can be the question directly asked. What is the distance between two nearest octahedral voids in FCC? Right? There can be one more question asked. The question can be, what is the distance between two nearest tetrahedral voids in FCC? So first of all, do remember, have a look exactly which are the nearest tetrahedral voids in FCC. Understand properly. So again, this is one FCC which I'm drawing. Imagine that this is the FCC. Imagine that the edge length of this particular cube is A. Imagine that the edge length of this particular cube is A. Now guys, have a look. For example, this is the front face. I'm selecting one of its corners. I'm selecting the back face and the opposite corner. Join them. It's a body diagonal. It is a body diagonal. At 1/4 of the body diagonal, what do we get? At 1/4 of the body diagonal, we get a tetrahedral void. So a tetrahedral void will be here. It is 1/4 of the body diagonal. Even here, right? 1/4 of the body diagonal. Perfect. Right? This is one tetrahedral void. This will be one more tetrahedral void. Isn't that 1/4 of the body diagonal? Right? Similarly, if you, for example, do one more thing. See guys. For example, if you select the front face and its top left corner, back face and its bottom right corner, if you join them, this is one more body diagonal. This is one more body diagonal. This is 1/4 of the body diagonal. Even this is 1/4 of the body diagonal. This is a tetrahedral void. Even this is a tetrahedral void. Okay. Now, which one are the two nearest tetrahedral voids? Dear students, this particular tetrahedral void and this particular tetrahedral void. These are going to be the two nearest tetrahedral voids. We need to get the distance between these two. That means we have to get this particular distance. Okay. So let's say this is the center of this particular edge, right? So if from here to here it's A, from here to here it's going to be A by 2. If from here to here it's A, right? Then from here till here it's A by 2. Then from here till here it's A by 4. So this distance is A by 4, this distance is A by 4. So A by 4 plus A by 4. Let me call this as point A. Let me call this as point B. So this particular distance between two nearest tetrahedral voids, it's going to be A by 4 plus A by 4. A by 4 plus A divided by 4. It's 2 times A by 4, which comes out to be A by 2. So A by 2 is the distance between the two nearest tetrahedral voids in case of FCC. You have to remember this as well. This can be the direct question asked. I hope you're getting what I'm saying. Is this clear? So what is the distance between two nearest octahedral voids, it's A by root 2. Distance between two nearest tetrahedral voids, it's A by 2. Correct, guys? Perfect. Okay, for example, if I ask you a question like this, what is the distance between two tetrahedral voids? Between two tetrahedral voids present on the same body diagonal. Present on the same body diagonal. Two tetrahedral voids present on the same body diagonal. What do you think? Quickly. So what I'll be doing, I'll be making one FCC. This is an FCC here, right? I'll be drawing one body diagonal. Let's say from here to here, it's a body diagonal, correct? 1/4, 1/4. These are two tetrahedral voids. What is the distance between two tetrahedral voids present on the same body diagonal? That means they're asking about the distance from here to here. First of all, you know, body diagonal length, let me call this as A, let me call this as B. Body diagonal length in a cube is always equal to root 3a. We have discussed that in BCC, if you remember. It is root 3a, correct? So the distance from A to B is root of 3a. The distance from A till center is going to be root of 3a by 2. From here till here, it's going to be root of 3a divided by 2. From here till here, it's going to be root of 3a divided by 4. So this is root of 3a by 4. This is root of 3a by 4. Even this is root of 3a by 4. So I can say the distance between two tetrahedral voids from here till here, right? How much is it going to be? Root 3a by 4 plus root 3 by 4 plus root 3a by 4, which comes out to be equal to root 3a divided by 2, right? So it's going to be a root of 3a divided by 2. Is this clear? Yeah? Is this clear to everyone? It's going to be root of 3a divided by 2. So do remember all these three terms. Number one, distance between two nearest octahedral voids, which we calculate a by root 2. Two nearest tetrahedral voids. The first one was two nearest octahedral voids, right? That was the first one. Okay, that was a by root 2. Then we talked about two nearest tetrahedral voids, a by 2. Distance between two tetrahedral voids present on the same body diagonal. It's going to be root of 3a divided by 2. I hope this is also clear. Now let's try to see what kind of questions can be asked now. Understand properly how exactly you are going to utilize these concepts in the question. For example, you have got a question like this. Let's say you have got a solid in which the constituent particles are A, B, C, and D, right? Let's say A, B, C, and D, these are the constituent particles. And it's mentioned that the solid is forming CCP, cubic closed packing, the FCC. The solid is forming cubic closed packed structure. A solid ABCD is forming cubic closed packed structure, in which A particles are at corners, B particles occupy octahedral voids, C particles occupy tetrahedral voids, and D particles, they are present at face centers. The question is, what is the formula of the compound? Can you solve it? What is the formula of the compound? See how exactly you are going to deal with these questions. It's mentioned that ABCD, it's forming CCP. What is CCP? CCP is nothing, that's FCC. And for FCC, what is the value of Z? Z value is 4. If Z is 4, how many total octahedral voids will be there? 4. How many total tetrahedral voids are there? 8. We know it. Number of octahedral voids is equal to Z. Number of tetrahedral voids is equal to 2 times Z. Now guys, A particles are present at the corners. Corner contribution is 1/8. There are total 8 corners. B particles occupy octahedral voids. In total, there are 4 octahedral voids. And all these 4 octahedral voids are being occupied by B. That means, if all the 4 octahedral voids are occupied by B, that means there will be 4 B particles in the solid, right? C at tetrahedral voids. Tetrahedral voids in total are 8. So all the 8 tetrahedral voids are occupied by C. So 8 C particles directly. Face center. Contribution 1/2 multiplied by 6. So this value is 1. This value has to be 4. This is 8. This is 3. So the formula is going to be A1, B4, C8, B3. This is going to be the formula of the compound. Is this clear? Yeah? All right. Let's have a look on one more. For example, I'm making a equation like this. Let's say you've got a solid A, B, C, D. Solid A, B, C, D. Okay? It is again forming CCP. It's again forming CCP. A particles are present at corners. B particles are present at 50% of tetrahedral voids. C particles occupy 25% of octahedral voids. And D is present at face center. What is the formula of the compound? Can you give it a try now? Can you give it a try? So first of all, ABCD, it's forming CCP. For CCP, CCP means FCC. For FCC, the value of Z is 4. If the value of Z is 4, total octahedral voids, 4. Total tetrahedral voids, that has to be 8. Because whatever is the Z value, same octahedral voids. Twice of that, tetrahedral. Now, A is present at corner. Corner contribution is 1/8. Total 8 corners. Right? B particles at 50% of tetrahedral voids. 50% is 1/2. Tetrahedral voids in total are 8. So half of 8 are being occupied. 25% of octahedral voids. 25% is 1/4. So 1/4 of total octahedral voids are occupied. Right? 1/4 of total octahedral voids are occupied. Face center. Contribution 1/2. How many? 6. Right? Just solve it. This is 1. This is 4. This is 1. And this is 3. The formula has to be A1, B4, C1, D3. Anyone got this as the answer? Perfect. Wonderful. Clear? Clear, guys? Sorry? This is clear? Perfect. All right. One more question. Let's see if you can solve this or not. For example, yeah, one nice question I'm going to give you. Let me see if you can solve this. A solid has got A, B, C, and D particles, right? A particles, simply they are present at corners. B are present at octahedral voids. C at tetrahedral voids. D at face centers. Okay, and the solid is forming CCP structure, cubic close packed structure. Now the question says, if all the particles along one of the body diagonal planes, are removed, what will be the formula of the compound? Can you give it a try? Can you give it a try, guys? Can you give it a try quickly? First of all, understand. A is present at corner. B is present at octahedral void. Octahedral void means in FCC, octahedral voids are present at edge centers and body center. Correct? So actually, B particles are present at edge centers and at body center. Yeah? Right, people? Now C particles, they are present at tetrahedral void. Tetrahedral void means 1/8 of body diagonal. Tetrahedral void means 1/8 of body diagonal. Correct? This is understood. All these things we have discussed, yeah? See, B is present at octahedral voids. That means B particles are present at edge centers and at the body center. C particles are present at the tetrahedral voids. That means they're present at 1/8 of the body diagonal. Now, if all the particles along one of the body diagonal planes are removed. Now understand. First of all, imagine that this is a cube. Imagine that this is a cube. Okay, imagine this is a cube. Now let me talk about one body diagonal plane. Already we have discussed also. Imagine that this is the body diagonal plane I'm talking about. Imagine that this is the body diagonal plane I'm talking about. This body diagonal plane. This body diagonal plane, right? Now, my dear students, one important thing. Understand. This body diagonal plane, it passes through 4 corners. So, all the particles along a body diagonal plane. That means, first of all, you have to remove 4 corner particles. These 4 corner particles, right? Number 1. Number 2. You have to remove these 2 edge-centered particles as well. Because the body diagonal plane is passing through these 2 edge centers. So you have to remove these 2 edge-centered particles as well. Correct? At the same time, this body diagonal plane, it is passing through the front face center. This is the front face center. This is the front face. It is its center. Back face, its center. So body diagonal plane, it's passing through 2 face-centered particles as well. Okay? What are the other particles? Have a look. The body diagonal plane is passing through the body center as well. One body center as well. Right? At the same time, if you join this with this, I'll be calling this as body diagonal. At 1/4 of it, you will find it tetrahedral wide. At 1/4, you will find it tetrahedral wide. So on one body diagonal, 2 tetrahedral wides. So on 2 body diagonals, total 4 tetrahedral wides. So 4 tetrahedral wides, 4 particles occupying the tetrahedral wides. They are to be removed as well. Yeah. So what is the formula of the compound then? Have a look. A is present at the corners. Corner contribution 1/8. In total, there are 8 corners. Out of 8, 4 corners are being removed. So I'll be left with only 4 corners. Right? B particles are present at edge centers and body center. Edge center contribution is 1/4. In total, 12 edge centers are there. But out of 12, 2 are being removed. So I'll be left with only 10. Right? At the same time, body center, contribution 1. And this body centered particle is already removed. So nothing. Right? P particles are present at tetrahedral wides. In total, there are 8 tetrahedral wides, out of which you have to remove 4. So only 4 will be left. Face center, contribution 1/2. In total, there are 6. Out of 6, 2 are being removed. So 4 are left. So what is the formula then? It has to be 1/2. This has to be 5/2. This has to be 4. This has to be 2. So take the LCM of the denominators, which is 2, multiply throughout by 2. So this is 1. This can be 5. This is 8. This is 4. So the formula is going to be A1, B5, C8, and D4. Right? First of all, this is the difficult question which can be asked in your NEET. These kind of questions used to be asked in JEE examination. Okay? But in your NEET examination, you'll be getting simple questions only. You need not worry about that. So tell me if everything is clear till here. Tell me if everything is clear till here. Everyone, I want you guys to let me know quickly in the chats. Every one of you. Every one of you. Every one of you quickly in the chat. Say yes or no quickly. Quickly, guys. Tell me what is the formula of this particular compound. It's a structure that's given. The question is like this. Right? Edge center, body center. And rest you can see. Circle represents M, square represents N. What should be the formula? Quickly. Quickly, people, everyone. What should be the formula of this compound? See, in this particular compound, you have got 2 elements, M and N. M is represented by a circle, and circles are everywhere at the corner. Contribution 1 by 8, total 8 corners. See what kind of simple question this is. N. N is present at 2 edge centers and body center. Body center's contribution is 1 multiplied by 1 plus edge center contribution is 1 by 2. Sorry, 1 by 4. And how many edge centers are being occupied? 2 edge centers are being occupied, right? So this is going to be 1. This is going to be 1 plus 1 by 2, 3 by 2. Perfect. So multiplying this with 2, this with 2. This is going to be 2. This is going to be 3. So M2, N3 is going to be the formula of this particular compound as well. Is this clear? Is this question clear to you? It should be clear to everyone. Now guys, there is one topic which is really formula based, and you are asked that as well. What is that? It is density. Calculation of density of units. I'm not going to derive the result, I'm just going to give you the result, because every time it's going to be a formula based question on density. Okay? Density of the unit cell, how do you calculate it? Z multiplied by M divided by Na multiplied by A cube. Now what these terminologies exactly are all about? Z represents the rank of the unit cell. What is M? M represents the molar mass of the substance which is forming the unit cell. Na is the Avogadro's number. A is the edge length. A is the edge length, for example, right? Now, let's say you have got a simple cubic unit cell. In case of simple cubic unit cell, the value of Z is 1. R is equal to A divided by 2. If you want to use the density result for SCC, simple cubic unit cell. So density of simple cubic unit cell is equal to Z value 1, right? M is the molar mass of the substance which is forming this unit cell divided by Na, and instead of A cube, what you have to write? 2R ka cube, which is 8R cube. Perfect. Similarly, you can use this particular result in all the other unit cells as well. You have got FCC, for example. For FCC, the value of Z is 4, right? And R is equal to A divided by 2 root 2. Something which you already know. Now you know density of FCC has to be equal to Z value is 4 multiplied by M divided by Na multiplied by A cube. A is 2 root 2 ka cube. Right? This is how you can calculate density of FCC. And these questions will be all the time formula based only. Whenever a question related to density is asked, it will be directly formula based, nothing else. Okay? In your NEET examination, I'm saying. For example, you have got BCC. In case of BCC, you have to put the value of Z as 2, right? Perfect. These are the simplest questions which are asked basically from the chapter solid state, if the question is asked. If the question is asked out of it. Perfect. All clear, guys? All right. If this is clear to you, let's have a look on one more thing. I'm marking the heading as ionic crystal. I'm marking the heading as ionic crystal. Or let me just write ionic solid. Let me just write ionic solid. Ionic solid. My dear students, ionic solid, first of all, I'm representing, for example, like this, AB. Let's say AB is an ionic solid, like NaCl. AB is an ionic solid like NaCl, in which this is cation and this is Ni. A positive, B negative. Perfect. Do remember, whenever we talk about ionic solids, in case of ionic solids, the larger sized ions, what do they form? They form the lattice. And smaller sized ions, they occupy the voids. This is one more important point. Whenever you talk about the ionic solids, in case of ionic solids, you'll find one ion will be smaller, one ion will be larger. And in generally what you'll observe, radius of cation, generally what you'll observe that cation is smaller in size than that of anion, right? In general, cation is smaller than anion, right? But there are exceptions as well in which cation is greater than that of anion. Okay, there are exceptions. First of all, whenever we talk about ionic compounds, in case of ionic compounds, there will be two ions. One will be smaller size, one will be larger size. In general, cation will be smaller, anion will be larger. Larger sized ion, it will be forming the lattice, and smaller sized ion will be occupying the void. Now the point is, which type of void the smaller sized ion will occupy? That's the point. Which type of void smaller sized ion is going to occupy? My dear students, in order to decide which type of void the smaller sized ion is going to occupy, I'm going to define a term. That's something which you call as the radius ratio. Radius ratio of the ionic compound is defined as the radius of cation to that of radius of anion. This particular ratio is something which you call as the radius ratio. If you know the radius of cation, if you know the radius of anion, you can calculate radius ratio of the ionic compound. You can calculate radius ratio of the ionic compound. Now, dear students, you have to remember one simple thing. If the radius ratio of an ionic compound comes out to be greater or equal to 0.155, less than, or this table is already made, I guess, here. Just a second. Let me make it. If the radius ratio is greater or equal, if the radius ratio of ionic compound is greater or equal to 0.155, less than 0.225. If the radius ratio of ionic compound, it comes out to be greater or equal to 0.155, less than 0.225. At that point of time, the smaller sized ion in the ionic compound will be occupying smaller sized ion occupies trigonal void. Do you remember what is the radius of the trigonal void? Sorry. Do you remember what is the coordination number of the trigonal void? It was 3. And if the smaller sized ion, if the cation perfectly fits the trigonal void, its coordination number has to be 3. Right? I was telling you one simple thing. When you talk about ionic solids, there is cation, there is anion. Right? In general, cation is smaller size, anion is larger sized. In general, you'll observe that larger sized ion, they'll form the lattice basically. They'll be present at the lattice points. Smaller sized ions, they'll be occupying the voids. Now the point is, whether smaller sized ion, it is occupying the trigonal void, tetrahedral, octahedral, or whatever. That depends on what? That depends on the radius ratio of that. If the radius ratio value comes out to be in this range, that means the smaller sized ion, it will be occupying the trigonal void, whose coordination number is 3. Right? By chance, if the radius ratio of the ionic compound comes out to be greater or equal to 0.225, less than 0.414. That means the smaller sized ion is going to occupy the tetrahedral void. Right? Coordination number of tetrahedral void is 4. And the smaller sized ion which exactly fits the tetrahedral void, its coordination number has to be 4 as well. Right? Similarly, if the radius ratio has to be 0.414 less than 0.732, the smaller sized ion is going to occupy the octahedral void, whose coordination number is 6, right? And similarly, if the radius ratio value comes out to be in this range, 732 to 1, the smaller sized ion, it occupies the cubic void, wherein the coordination number exactly is 8, right? So, in short, for example, I'm giving you an ionic compound. Let's say you've got an ionic compound like this, AB, A positive, B negative. Let's say I'm giving you the radius of cation value. I'm giving you the radius of anion value as well. I'm telling you what is the radius of cation, what is the radius of anion. Can't you calculate radius ratio for this ionic compound? Absolutely. R positive divided by R negative. That will give me radius ratio. And when you get the radius ratio, you have to look at this particular table. You'll get to know exactly in which void the smaller sized ion will go. Yeah? Perfect? Right, guys? This is something I'm talking about, right? And do remember their examples as well. These are the common examples of it which you need to remember. Perfect? Perfect, guys. You have to remember these examples as well. This is something which I was talking about till now. Okay? Is it clear to everyone? Quickly let me know in the chats. All clear? All clear, guys? Quickly tell me everything is clear. Say yes or no. How many times I'll tell solid state is deleted from NCERT, still in the syllabus of, right? There is no announcement about the deleted chapters as far as NEET examinations. There is no announcement. It's only mentioned that solid state chapter is deleted from NCERT. NEET, it is still there. If notification comes, then you'll get to know. Okay? I cannot repeat the same thing again and again. All right, let's have a look on structures of ionic compounds. There are only two topics left basically here now. One is structures of ionic compounds and one is defects. Both are very simple topics, small topics, right? Okay, let's see exactly what do we have to remember about them. And these topics, these two are basically memory based most of the times. Okay, structures of ionic compounds. My dear students, in case of ionic compounds, we start with NaCl structure. NaCl structure. Just tell me one thing, in case of NaCl, what kind of ions do we have? We have got Cl negative ion, we have got Na positive. These are the two different types of ions which we have in case of NaCl, right? Particularly when we talk about NaCl structure, Cl negatives, what do? They form FCC. That means Cl negatives are present at corners and face centers. Na positives, they occupy all the octahedral whites. Now guys, if Cl negative is forming FCC, for FCC the value of Z is 4. If the value of Z is 4, that means in order to make an NaCl type structure, we would need 4 Cl negative. How many Na positives do we need? See, for FCC, Z is 4. If Z is 4, that means octahedral whites will be 4 in total. And all the octahedral whites are being occupied by Na positives. So we need 4 Na positives as well. So in order to make a structure like NaCl, we need 4 Na positives, we need 4 Cl negative. Point number 1. Point number 2. Now these 4 Na positives and 4 Cl negatives, from where you are going to get them? I'll say, if I take 4 formula units of NaCl, 4 formula units of NaCl will give me 4 Na positives and 4 Cl negatives, which are enough to make NaCl type structure. So this can be asked. How many formula units? How many formula units of NaCl are there? 4 formula units. Okay. Do remember the coordination number of Na positive as well as Cl negative. In the structure, that is 6:6. This can be asked as well. Either formula units will be asked or the ratio of coordination will be asked. Or simply they'll ask you about the occupancy of the ions. Where is the Cl negative present? Where is the Na positive present? Right? Anything about these things can be asked. I hope it's clear. Just these things you have to remember. Any Cl negatives, they form FCC. They are present at corners and face centers. For FCCs, that is 4. That means there should be 4 Cl negative, right? If Z is 4, 4 octahedral whites. All the octahedral whites, Na positive. So 4 octahedral whites are occupied by Na positive. So in order to make a structure like NaCl, we need 4 Na positives, 4 Cl negative. Now from where they will come? They'll come from 4 formula units of NaCl. So 4 formula units of NaCl are enough to make it. Number 1. Number 2, coordination ratio 6:6. You can, this value is not important. It is not important, right? It is not important. You can remember one thing only. Since you got to know Na positive is present at octahedral wide. If Na positive is present at octahedral wide, what should be the radius ratio of NaCl? In which range it should lie? In which range it should lie? The term is octahedral here. The term is octahedral. And I told you a few minutes back. Right? This should be, NaCl, its radius ratio has to be in the range of this. Perfect? It has to be in the range of this. Now, my dear students, there is one more structure. That's what you call a cesium chloride structure. There are a lot of structures basically, but you have to remember few only as far as your NEET. Otherwise, there are a lot. First of all, cesium chloride structure. In case of cesium chloride, you have got Cs positive and Cl negative. These are the two different ions which we have. My dear students, Cl negative, in case of cesium chloride structure, they are present at the corners of the cube. And Cs positive, it is present at the center of the cube. Or I'll say Cs positive occupies the cubic void. It occupies the cubic void. Yeah. So, if Cs positive is present at the center of the cube and Cl negative occupies the corners of the cube, corner contribution is 1 by 8 multiplied by 8. The value comes out to be 1. So, in order to make a cesium chloride structure, how many Cl negatives do we need? 1. Center of cube, contribution 1, and there is only 1. The value comes out to be 1. So, I need 1 Cs positive as well. So, in order to form a cesium chloride structure, I need 1 Cs positive, 1 Cl negative. You tell me, where do I get 1 Cs positive, 1 Cl negative? If I have one formula unit of CsCl, which dissociates into 1 Cs positive, 1 Cl negative. And once I get 1 Cs positive, 1 Cl negative, I can make this kind of a structure. So, how many formula units of cesium chloride are required to make this particular structure? 1 formula unit, right? If they ask you about the coordination ratio, it is 8:8. It's 8:8. You can see Cs positive is occupying cubic void. If you remember cubic void, its coordination number was 8. And any particle which enters the cubic void, its coordination number will be also 8. So it's 8:8 basically. It is 8:8. Perfect. If you have a look over here, for example, Cl negatives, they are present at corners. Let's say these are Cl negatives which are present at the corners. Perfect. This is Na positive at the center. Right? Na positive at the center. Its neighbors are all the corner particles which are equidistant from Na positive. Na positive's neighbors, immediate neighbors are all the corner particles. So total 8 corner particles, which at every corner there is Cl negative present. So in total, how many immediate neighbors it has? How many nearest neighbors it has? 8. So Na positive, its coordination number has to be, sorry, not Na positive, it's Cs positive. Cs positive, its coordination number has to be 8. Similarly, Cl negative. If you talk about Cl negative, its coordination number will be 8 as well. Because its nearest neighbor will be Na positive. One more Na positive here in one more cube. One more Na positive behind the cube. One more N positive. One more Cs positive in one more cube. Right? Similarly, 4 more at the top. The way I discussed BCC with you, the way we discussed the coordination number of the body-centered particle in BCC, in the similar way you can check it out here. Yeah? Right? It's simple, guys. This is Cs positive here. This is Cs positive. And all these corners are Cl negative. All these Cl negatives are equidistant from Cs positive. So 8 coordination number of Cs positive. Right? Similarly, if you want to calculate the coordination number of Cl negative, this corner particle, right? You have to count Cs positives. This is one Cs positive here. One more Cs positive at the center of one more cube. one more at the center of one more. So 4 in ground floor, 4 in top floor at the center of each cube. So in total 8. So 8 is to 8 is the coordination number. I hope it's clear. So these things you have to remember about what? Cesium chloride. Now guys, there is one more, that is zinc sulfide. It forms two structures. One is sphalerite, one is wurtzite. Sphalerite, wurtzite. And these are the things which you just have to remember about. That's all. Nothing else. That's all. Right? The way we do things for, the way we did things for NaCl and cesium chloride, in the similar way, these two things you have to remember about zinc sulfide. This is the structure of your sphalerite, structure of your wurtzite. Right? Perfect. Basically, in sphalerite structure, your S-di-negative ions, they form FCC. And Zn di-positives, they are present at half of tetrahedral voids. Similarly, in wurtzite structure, your S-di-negatives, they form hexagonal closed packed structure, HCP. And your Zn di-positives, they are present again at half of tetrahedral voids. And eventually, you just have to remember the formula and all, right? Coordination ratio, all these things. Anything can be asked out of these things. Similarly, there are two more structures which you have to remember. One is CF2 fluoride structure, AB2 type. Remember the occupancy, where are these ions present, and what is the, each Ca di positive is surrounded by 8 F negatives, and each F negative is surrounded by 4 Ca di positive, right? Similarly, this is the last structure, that is anti-fluoride structure. You have to remember the occupancy, formula units, and coordination ratio. That's all. That's all. Yeah? Perfect. Furkana, which are you talking about? Are you talking about zinc sulfide? In case of zinc sulfide, Zn di-positive occupy alternate tetrahedral voids. That means half of tetrahedral. Okay? In both the structures, whether you talk about the sphalerite or wurtzite. Perfect. So my dear students, 95% of the chapter is done till here. There is 5% left, that is defects. But I won't continue defects now. I'll post a recording like of half an hour for the topic defects, right? Maybe tomorrow or day after tomorrow. I'll post a recording on the same channel regarding the defects. Perfect. Is that cool? Because that's complete theoretical topic. Complete theoretical. Or you can do the defects on your own as well. Whatever is feasible for you. Right? Like Schottky defect, Frankel defect. Anyways, I'm going to share these slides with you. Okay, metal excess. That was it. So I'm going to make one small video of the topic defects so that it will be again clear to you if any one of you will be having any sort of doubt. Right? Just one more type of question I would want to share with you, then we'll finish the session, okay? Maybe you'll find these questions also. And what the question is, you'll find this kind of the question. For example, I'm writing Fe 0.930. In solid state only, you'll find it, okay? And they'll ask you to calculate the number of Fe di-positive ions. The number of Fe di-positive ions in this particular compound. How do we exactly solve this question? My dear students, iron exhibits in Fe di-positive oxidation state as well as Fe tri-positive. Let's assume there are X Fe di-positive ions and these will be in total 0.93. So it's going to be 0.9396, right? It's going to be 0.9396. I'm assuming that there are X Fe di-positives, total are 0.93, out of which Fe tri-positive will be 0.9396, right? If I use the charge conservation principle, the charge conservation principle says charge on this plus charge on this has to be 0, right? What is the charge present on iron over here? Iron exists in two oxidation states. Fe di-positive, these are X. Fe tri-positive, these are 0.9396. What is the charge present on Fe di-positives? It's going to be plus 2 into X. Charge present on Fe total, all the Fe di-positives. Plus, what is the charge present on Fe tri-positives? 0.93 minus X multiplied by plus 3, right? So this is the total cationic charge, right? Plus, What is the charge present on oxygen? It's -2. Charge present on oxygen is -2. Net charge is 0. So can I say I got one equation which just contains one variable? You can get the value of x from here. Right? You would have seen these equations. Yeah? Perfect. For example, you have got a question like this. Let's say the question is Ni 0.980, and it's mentioned that nickel is exhibiting, it's showing two oxidation states, nickel di positive, for example, nickel tri positive. You are supposed to calculate how many Ni di positives are there. Let's assume that this is x, so this will be 0.98 minus 6. Use the charge conservation principle. Sum of all the charges is equal to 0. So the charge present on nickel di positive is +2. And how many are there? X plus. The charge present on nickel tri positive is +3. And how many are there? 0.98 minus 6. The charge present on oxygen is -2. The net charge has to be 0. One equation, one unknown. Get the value of x. That's something which they ask you, okay? Perfect. One question I'm going to give you. With that, you are going to let me know the answer of that question in the comment section right after the session. Okay? The question is like this. One simple question I'm going to give you. For example, the question is an alloy of copper Au and Ag, copper, gold and silver, right? An alloy of copper, gold and silver forms CCP, or let me write it as forms hexagonal close packed structure in 3D. Hexagonal close packed structure in 3D. It is hexagonal, okay? Z value 6. Hexagonal close packed structure in 3D. It is mentioned that copper, it is present at the corners of the hexagon. Au occupies all tetrahedral voids. Ag occupies all octahedral voids. I'm asking you to calculate the formula of the compound, the empirical formula of the compound. Can you give it a try and let me know its answer in the comment section? Yeah? Can you give it a try and let me know its answer in the comment section? Be careful with one thing. You might do one mistake here. It's mentioned that hexagonal close packed structure. So the structure is like this. So the structure is actually like this. Okay, this is the structure basically, in which copper atoms are present at corners. Copper is present at every corner here, every corner. So there are basically 12 corners, if you remember, 12 corners. And do you remember the contribution of each corner in the hexagon? It used to be 1/6. It was not 1/8. That was in cube. Perfect. Rest. Z value also, you know, that is 6 for the hexagon. So tetrahedral voids will be 2 times Z, octahedral voids will be Z. So you should give it a try. And do let me know its answer in the comment section of this particular. My dear students, the next chapter, which we are going to start, that's going to be chemical bonding. And chemical bonding we shall be doing on Monday. Chemical bonding chapter, I'll be giving 2 sessions for that particular chapter because that's huge. It's a big chapter, right? So in 2 sessions, your entire chemical bonding, I'll be finishing off. Okay, so I want you guys to join all the live sessions with me, right? So Tuesday, it's going to be chemical bonding at 5 p.m. We shall finish almost 50% of the chemical bonding chapter that day itself with the theory, with all the problem patterns and everything. Okay, so let's complete the entire syllabus in just 6 months, and after that, we'll start the crash course, revisions, everything. Okay, perfect, guys. So with this, I'll be taking a leave. Take care. God bless you all. See you in the next session. Bye-bye. Take care, guys. Bye-bye.